provides a development environment for user in order to create complete, ready-to-deploy applications, software applications. Graphical user interface are used, and configuration are available to users so that they are able to configure the whole application, possibly avoiding the complexity of encoded programming. So this is the definition given in Wikipedia, but as you know, this is a recurrent research meeting, and we have a YouTube channel where this topic has been already introduced many times by our colleagues and member of the Lowcomote project. So we kindly invite you, if you want to know more about the low-code development platform and how they are, let's say, studied in this research project, you can really subscribe to the Lowcomote YouTube channel. You see here the link. So, and as I said before, the Lowcomote is a European project, and the goal is to train the next generation of professionals that will work in designing the new low-code development platform. Well, and the goal is to overcome the current limitations that you can see in the heterogeneous landscape of low-code development platforms. And these known limitations are usually scalability, a bit of fragmentation, and in particular, low-code development platforms are usually adopted for creating a software application. So the application domain is currently a bit, oops, let me remove this, is a bit, let's say, limited to software intense application, let's say. And the goal in Lowcomote project is to adopt state-of-the-art model-driven engineering techniques and practice, as well as machine learning algorithm and cloud computing, in order to improve and then obtain the next generation of low-code engineering platforms, let's say. And here in these slides, you can see, let's say, also the partners that industrial and academic partners that are taking part to the project. So let me now introduce the workshop. Today we have both industrial and academic speakers from companies and academic institutions. And in the next slides, I can just introduce you briefly the agenda for today. In the morning, we have the industrial speakers and industrial talks, while in the afternoon session we will go with the academic talks. So after my brief introduction, I'm going to conclude very soon. The first speaker is Alfonso Diez by uGround, and then we go ahead with the IncQuery Labs. Then there will be a short break until 11. Then we'll go ahead with the third speaker by Dynatrace, and we will then have a short discussion after the industrial talks. Then we will have a lunch break of 1 hour and a half, and we will continue then with the afternoon session with 2 talks. Around 3 p.m. we will conclude the workshop with a 15 minutes discussion and wrap-up session. And yeah, so as you can see from the schedule, each speaker has 45 minutes for his talk, and he can split it in half an hour of presentation, 50 minutes for the question-answer session. But then, of course, the speaker is also free to take some more minutes to conclude let's say, the talk. So that's all from my side. I want to leave the stage to the first speaker, that is Alfonso Diez by uGround. And yep, so let me stop sharing the screen. And
okay,
Mr. Fons, let me know if you are able to share yours.
yes, I am working on that. Good morning to everybody. um, just a second. Let me see if I can. Okay, can show this. Okay, let me know if I'm sharing the screen. I think so.
Yes, it works.
Okay, so let me minimize this. Okay, great. So good morning to everybody. I am Alfonso Diez, CEO of EURound. Our company works in the field of model-driven engineering since 10 years ago, or probably more. And we have approached the problem of semantic modeling or model-driven engineering from rather a new point of view. And I am going to introduce to you how we work and some ideas about how to mix semantic modeling or model-driven engineering based on semantic structures with complexity theories in order to cope with a serious problem that we have today that is driving digital transformation. That is, the motivation of my talk, and this is something I will talk about in the next minutes. Well, tomorrow, my presentation today is going to be only theoretical. I mean, there is no practical part on it, but tomorrow, Pablo, that is our CTO, will introduce our technical part, and we will build some examples of this or everything that I am going to show you today. So. In order to introduce the ideas, I would like to show, to introduce Jules Verne, that 150 years ago wrote or published a book titled 5 Weeks in a Balloon. And that book was related with the way to find the source of the Nile River. The problem at that time was that finding the sources of the Nile was a very difficult and dangerous travel, because it was an unknown place full of tribes and full of dangers and animals and things like that, and it was really difficult, expensive, dangerous to find the source of the Nile. So they decided to change the layer. So instead of going by the earth, walking, they decided to go by the earth and in a balloon. And it's a way of finding a new way to do something cheaper, faster, and safer. That is very important. So this idea of the balloon, I am going to use that metaphor in order to follow my presentation, because I think it's important to realize that we can work at different layers of different layers, and we can obtain different results depending on which layer we are. So the motivation of this talk is related with a fact, that is the creation of information technologies today is a difficult task for companies. I mean, we have been programming since 50s and creating very large information systems since 80s in the past century. And programming is increasingly a more dangerous, difficult, expensive, fragile way of doing things. And now we are in a process of an ongoing massive digital transformation. We are creating more and more technologies, more and more complexity. We have less time for doing that, and we have less money. And this is creating a very complicated situation for enterprises. So in order to solve the problem, we need a balloon. We need to change the layers. It's clear that producing code is not the solution, and producing more and more code is not the solution. So we need to think in a different way, so we can solve the problem of creating information systems or business solutions at a large scale for larger organizations, not at a small scale. So this is the idea of the motivation of everything I'm going to show you today. I am going to use matryoshkas to show you the different layers of the problem of creating model-driven systems, based systems at large scale. The first matryoshka we are going to show is the first envelope of the matryoshka. The first layer is our enterprises are critical systems. Let's think about what is an organization, what is a company, enterprise, a public agency. What is an organization, a human organization? If we take a look at an organization in a given moment of time, in each moment of time, you will see a machine, because it works in a precise way. It has a given set of procedures, have people, produce a kind of products in a given way, delivers that products or services to in a given form. It has a given set of people on it. But this idea of the company as a machine, it changes when you look at the company on time. If you take a look at the company each week or each month or each year, you will see changes, continuous changes in people, in processes, in procedures, in technologies, in products, in channels. Everything is going to change in the company because the company needs to adapt to new situations continuously. So as we see on time, a company is an autonomous, self-organized system with an internal state that is changing continuously. This is the idea that companies are critical systems that are moving all the time by themselves in a self-organized way. The idea is, this is our goal, is to support the organization in this way. So as an organization is a critical system, we see that has four properties, key properties for every system. Every system has these four properties. The first of all is identity. The system has an inner part and an outer part, and they are clearly differentiated. Then the second property is continuity. The system wants to be alive, is trying to continue on time, wants to be there the next year and the next year. And this means that the company is going to develop mechanism to be able to do that. Then the companies or the organizations, the systems have what is called operational closure. That means that the organization, the system, is going to produce things, is going to have some kind of metabolism that is going to be done internally within the structure, the boundary of the company. And then we have another property that is structural coupling. That means that the company or the organization or the system is going to have a mechanism to change continuously to adapt to new changing situations in the environment, or to change the environment to create good situations for itself. Let's say, for instance, if I am a company, I can make a marketing campaign in order to change the way my customers think about my products and sell more. So I am changing the environment in order to get an advantage. So those are ideas about critical systems. So what we see in summary is that any organization is an entity that has a metabolism and is going to change, is prone to change. It will change continuously. So technologies have to have the same thing, because if not, they cannot serve organizations. So and technologies has to be oriented to metabolism, to be able to represent the metabolic paths of organizations, and it has to be easy to change. You can change everything within the technology in an organization to adapt it to the needs of change of the organization in its environment. Conventional technologies, as we have said, they are like trying the Nile sources working. It's not, they don't work in this moment of time, and no more anymore. So we are proposing digital twins for organizations as our balloon, what we are going to use to create this new layer. So DTOs, digital twins for organizations, is not our second part, or second layer. And what is a DTO? Well, a DTO, a digital twin organizational, is a standard technology. It's a horizontal technological platform that is able to represent, to serve any part, any aspect of an organization. It's able to work with the people, with the assets, with operations, with governance. Everything that a company contains or does can be represented by a DTO. Hence, the DTO is able to monitor, to simulate, to orchestrate everything that happens in the company, including any existing information system. So everything that happens in a company can be supported up to some point by a DTO. a DTO evolves not by programming, but by configuration or by modeling. So we tell the DTO what we want. We tell the DTO how we work, what we pursue, and the DTO is able to recognize what we want and to adapt to it and execute it. And that means that the DTO is able to design itself in the sense that receives realities and adapts to the reality in a dynamic way. So it designs itself and enacts itself that design. So it's this idea that the DTO is able to represent itself as part of the company means that the DTO has to have some strange technical characteristics. That means that the DTO has to be able to analyze its own functioning. So this means that it needs a semantic structural, self-referential design and an active design. That means that the design of the DTO is able to understand its own design and put it, enact it as an information system. That means that the DTO has a recursive way of developing and a self-organized and autonomous execution. We have, Juan de Lara and me have published some weeks ago an article detailing all these things, because this is, I mean, it's an extended set of ideas, and I recommend you, if you are interested in DTOs, to read this paper. So we have been talking about organizations as critical systems, and DTOs as or balloon or technological solution for running enterprises. But we need a mechanism to tell the DTO what we want, because I have a technology that is able to run any description of an organization, but I need a mechanism to describe my organization. So we're going to use semantic-based engineering that as the language that we are going to use to communicate people with DTOs. So let's see this third envelope, the semantic-based engineering. Well, semantic-based engineering is based on the fact that in society is built with two main components. One is people, minds, and the other one are languages, because the languages are the way that we use to be able to communicate minds. Minds have concepts, we think about things, but we use languages to communicate, to interact, to share concepts. And society is built on top of people, minds, and languages that are communicated ideas, shared concepts. Organizations are always language-driven. We tell each other what we want, how we work, what we are doing. The society is language-driven all the time. So at the end, languages are the path, the way we use to communicate knowledge and to represent knowledge that is part of our minds, because the knowledge is within our minds, not in the language. So there is a mechanism of interaction between minds and languages as continuous interaction. So semantic engineering is an engineering based in the capture of conceptual representations. So our minds have concepts that we share with languages, and we are using semantic engineering to take that concepts, to represent that concepts in a proper way, and to create information systems. How are we going to do that? Well, let's see this diagram. We are saying that we have realities, human realities. For instance, we have conferences and talks and invoices and whatever, or reality in the company. And people is living in this reality and is creating also the reality, is changing the reality in every day. And they change the reality talking about the reality. What we are going to do is to capture the concepts of the reality and represent that concepts in terms of ontologies, formal ontologies. Ontologies about courses or invoices or human relationships or whatever we do in our reality. So we can create with ontological representation formal structures of the reality. That ontological representations can be sent to a DTO that is able to interpret that formal representation and enact an information system that is a solution for the reality, that represents that reality in a technical way, because the DTO is a technology. So this method allows us to create any solution based on ontological representations. And it is very important to see that when we do this, the enaction of the DTO that is represented using a representation of the reality becomes a part of the reality. So the reality with the DTO is a different reality. So it's a changed reality. So we can represent this new reality that will enter into the DTO, and that means that we are creating a cycle, a dynamic cycle of evolution, where humans and digital twins are working together to create new cyber physical ways of doing, so digital organizations. Okay, so now we have a mechanism to create representations that can be interpreted by a DTO. We will see something much more about this in the next slides. But we are talking about organizations, and an organization is not any reality. It's a reality that has an economical structure, is based on hierarchies and on business processes, on value creation. It's not any possibility, but a very specific way of thinking. So how do we represent the ideas of companies or enterprises? So we are going to use complex adaptive systems and agent-based ontologies as a subset of semantic engineering that is applied only for organizations. So we can speed up the way we analyze an organization and create information for them. So this is our fourth envelope, complex adaptive systems. Okay, so let's say a conventional enterprise. A conventional enterprise is people that is doing things. I mean, they are working. They go to work and they do things that are in their domain. Even they use computers in many cases to do their work, to prepare things or create transactions or whatever they do. In a digital enterprise, that is our objective, what we have is things doing things. And I will show you an example right now that can imply people. So we have a kind of agency of digital twins that are able to understand the reality and to put the reality into functioning. And this functioning can imply people for doing things. So it's not people doing things, but things implying people. We are changing the way we are describing this analysis. So let's see an example. If you go to Amazon, and you click, you place your order, when you click that button, a lot of things happen in sequence and very fast. There is a stock manager mechanism that is going to analyze the stocks and generate transfer orders and picking orders, and those are going to generate packing orders and delivery plans, and then this generates delivery orders to get the package and send it to the end user, to the customer, and all these things will be also based or helped by account receivables agents to get the money, human resource planners to put the people, accountancy, and everything else. So when you click that button, everything happens, and a lot of agents, autonomous agents, are going to play together in a collaborative way to solve a complex problem. That is the problem of logistics of Amazon that is not simple at all. So you receive an experience that is really good. It's very fluid, very fast, very flexible. It works always. It's fantastic experience, but it works in a very automated way. It seems that it's a machine, but it's not a machine. It's a lot of small entities trying to solve the problem of sending something to somebody. If we take a deeper look at this, we are going to use an example, an impersonated invoice. So I'm taking an invoice and transforming this invoice in somebody. So hi, I am an invoice. Okay, I've been created by a process of billing And I have a context because I am part of a contract, and this contract is from a customer. So I have a relationship with a customer, and I have not been issued yet, but I want to be issued soon because it's my time. I need to be issued. And then I have a plan. Once I have been issued, then I will check if I am collected on time. I will do this and this and this. Otherwise, I will try to contact with the customer and will tell the collection department that I need to be collected, and so on and so on. Okay, so I want, as an invoice, I want to be happy and I want to fulfill my destiny because I have a destiny. I am something. I have a meaning, and this is very important. An invoice is not a data element; it's a meaning. It's something that wants to get something because it's important for the company. So when you think about the concept invoice, you don't think about data or table. You think about the agent invoice, somebody that wants to get an objective, a destiny, that is wants to be collected on time. Is my goal. So I'm going to do everything needed to get collected on time. So let's see at the company thinking on agents and not thinking on data. But it's rather different. So an agent has a complex structure. For instance, this agent, this invoice, first of all, is in a classification system because it is in a world of concepts, of semantics. And we think that a structure has a meaning, a purpose, a set of relations, a set of signals that can be received. It's in a classification system that is really important to create a proper domain for the agent. Then has a dynamic structure. Because it has states, has rules, procedures, BPMs, whatever. Those are the metabolic rules that the agent is going to follow. Then it has a lot of data entities. For instance, of course, the invoice data should be usually the invoice table, but it has also products, lines, activities, customers, addresses, whatever. Has technologies involved in its life cycle because it has mail and SQL and PDFs. The agent is going to use technologies to do things that are expected. The invoice is going to share information or activities with people, for instance, with the collection department or with other agents, for instance, with the accountant, with the collections or the pricing agent. So you can see that if we think in terms of agents, we see much more complexity in terms of a structure. Are the same structures, but we are not describing it in the same way that we used in the past. We are thinking about a complex adaptive system. We want to generate intelligent parts that are able to share information and events between them and try to obtain results. Well, as I've mentioned, agents are going to interrelate with third parties, with technologies, with people, with other agents, or with data. So what we do here is that we use interpreters, interpreter agents. Here we have an example. We have a functional agent that, let's say, the invoice, that wants to speak with an end user, wants to have an interaction with an end user, human. And what the functional agent is, in order to do that, is going to produce a set of data and metadata that is involved in the exchange, in the conversation, and an interpreter is going to generate something that is valid for the end user, let's say HTML or whatever, and the end user is going to interact with this. And if the end user does any kind of action, clicking, let's say, this action, this event, or this data is going to go to the interpreter that will pack it in terms of DSLs and send it to the functional agent backwards. So this technique of using interpreters based on ontological descriptions, this is an ontological description and this is an interpreter, and this is a third party, can be used for to solve not many, but all the needs for interrelation between agents or concepts, semantic concepts, and everything else. So it's a technique that can be generalized to solve any kind of technological requirement in a platform, in the DTO. Well, the basic properties of an agent that are built using semantic engineering. Basically, an agent is a concept that defines its meaning, teleology, and constitution. An agent always has a life cycle that establishes for what is the agent, what is the purpose. Also is always a data entity that can be very simple or very complex, structured or not. The agent has a boundary, so we know what is within the agent, and the agent is able to interact, as we have seen, with other with the external world in the boundary, using this kind of interpreters or signal processors. Then the agent is able to interrelate with many other players, and the agent knows about itself, is able to understand its own constitutions and dependencies, and that means that can be very intelligent in terms of if it's decision making or the application of rules. Well, this is an example, a very simple example that has been taken from the systems we use in Spain, in Uground. I'm sorry, it's in Spanish because it has not been translated. So I put some labels in order to simplify the understanding. But this is the final result of using a DTO and a semantic structure, an ontology to drive the DTO for doing something. In this case, we are going to solve the problem of incoming invoices, not the ongoing invoices, but the incoming invoices. So this is my example. It's a very simple example. In this example, what I have is a screen that is presenting information about an incoming invoice. And in this information, I have basic information, dates, additional information like the supplier or the order, amounts, and everything else. So we see information about this invoice. And here we have the state. The state of the invoice is matched with the bank. So if I want to see the payment of the invoice, I can see that the invoice has been paid, and this is the bank details from to, and those are data about the payment, how it was generated, what kind of payment, and everything else. So I can see the invoice and the payment also has an state that is justified, and in this case, what it has a meaning for internal meaning for the company. And then I can see not only the invoice and the payment, but I can see the procurement order in which the payment has been included. So I can see all the invoices that are related with this order. And I have here the data of the order, the invoices, documents, comments, and processes. I mean, rules or BPMs or whatever we have applied to this set. If I go to the process, I can see that how this order has been approved. In this case, is the approval of the order. Well, the diagram is really simple because it has only one task that is approved and can be done by people or in an automatic way. Can be a rule, an automatic rule to decide the approval of this order in this case. So even more, I can go to the supplier apps, and I can see the information about management of the incidents with the customer, with the supplier in this case, excuse me, or the documents I have exchanged with my supplier. And also I can see other orders for the same supplier. And if I go down to the order, I can see the processes, the documents, the invoices, the invoice details, the payments, and everything else. So all this set of data, information, screens, BPMs, state management, and everything else has been created using ontologies. So and DTOs, digital twins. So I have created an ontology about how we manage suppliers, orders, invoices, and payments. And this ontology has been added to the digital twin. So the digital twin knows about how my company works and is able to enact the ontology in real time. There is no source code production at all. It's real-time interpretation of the ontology. So it's time to change the ontology, to change the enacting system. It's a real-time mechanism. And tomorrow we will see it. So, summary. We are thinking organizations in terms of organizational metabolic paths. So we are saying that an organization is something that produces value, and producing value is a change of activities that is based on agents, and those agents are going to interact with other agents, with people, with technologies, or with semantic concepts in general terms. So we are seeing organizations in terms of complex adaptive ontologies embedded in semantic engineering that is going to be used or enacted by digital twins. So to wrap up, we have described a workable method to generate that kind of critical systems. In fact, we are using this method in our commercial activities, and we are working for large organizations in many countries, managing millions of transactions, tens of thousands of users, and very, very complex business problems. And this is workable. This really it's not theoretical, but this is workable. It's based, as we have seen, in the idea of DTOs that are managing semantic engineering that represent agents as the way of describing organizations. And this allows us to represent very, very complex organizations and processes. In fact, there is no limit in the size of the problem that we want to solve. We solve really very, very difficult problems in very large organizations, and it's done in a very standardized way. You only describe how the company works, and the DTO is able to understand that, and it works. So there's no creation of nothing. So finally, we have talked about layers. So at the end, we have 3 layers here, because the basic thing is the source code. So source code is the basic layer. On top of source code, we are working on low-code platforms, low-code development platforms that are a mechanism to avoid source code, or by generating source code, or by avoiding the generation of source code up to a point. Okay, so now we're proposing here the use of no-code DTO. So the DTOs are able to use interpretation of the reality without any kind of source code. So there is no code. It's only ontological descriptions that can be interpreted by DTOs in real time. And this technique scales without any limit. That is the good part of this idea. So, well, I finished. This is the question time. We have a lot of answers, I can promise you. Most of them complex.
Afonso, thanks a lot for your interesting talk. Yes, so we have around 10 minutes, almost 10 minutes for questions. So please raise your hands if you have any question, please. Otherwise, I have one for you. So, okay. So please, I see raised hand.
Yes, it's Panayotis here. Should I go ahead, or?
Please go ahead.
Okay. Yes, thank you for the presentation, first of all. Very interesting idea. I quite like it. I'm trying to understand, of course, it's a high-level presentation, right? So you on purpose didn't go into the technical details of how it all works. But because I'm curious now, you have piqued my curiosity. Maybe you could give us some insight as to how it will work in practice. Okay, don't go into very low-level details, but for example, you say by using ontologies, we define the purpose of these agents. But by our intuition, we know that at some point, some code is going to be executed. So could you maybe give us the intuition of how these layers connect with each other?
Yes. Well, what is the idea of the difference between low code and no code? Is a matter of domain, because when you represent knowledge, you have four techniques. One is plain text descriptions. The other one is drawings, blueprints, maps, diagrams. The other one is forms, templates, and the last one is recipes or algorithms. And always when you are representing knowledge, what you are going to, at the end, you are going to use some kind of recipes or algorithms. So and those are values usually are represented in terms of code. Okay, so at the end, there is some kind of code in some place. But the idea is, if you can introduce this coding, because you need to write some code in some moment, as part of your ontological description, not external to the system, but internal in the ontological description, and it's going to be a part of the interpretation of the DTO, the digital twin, you are putting in the closure of the digital twin not only the semantic structure, but also the procedural rules. They all are part of the architectural ontology. And this is the key point, because you don't have at this point and in this moment two worlds: the world of modeling and the world of programming, the world of modifying source code, the world of compiling. You don't have that. You have only one place to make all your descriptions about the reality. And you can use different techniques, but always within the ontology. And this is the key point to avoid, to say that it's a no code. No code doesn't mean that there is no algorithms. It means that the system is closed. Everything that happens in the DTO is within the ontology. There is nothing external at all. And this is the key point. I don't know if I've explained it.
Mm-hmm. So in other words, the system continuously, you don't get, let's say, you don't go from model to code, but there is a system that continuously interprets the model and does things.
And you use models to create models, because the ontology, the DTO ontology, can produce new ontologies that are added to the ontological base that produce a given functionality for the system. So the system creates itself continuously, and once you have created the basic set of technical set, the core technical set that is done with the conventional source code, what you get is that the system evolves itself in a recursive way without the need to create any kind of source code on top of that. So there is no more need of code. You always create new capabilities, extending ontologies, never programming things. This is the idea.
Of course, when the language engineer introduces a new concept into the ontology, it needs to match it with the code that will actually do the thing. Like if I say, the entity invoice can send late payment alert, then I need to write the code that sends the email or something like that.
Exactly. You have to program a number of interpreters. Interpreters are the connectors between the concepts and the external reality. But it is a finite world, because you have, let's say 100 interpreters, and then once you have the 100 interpreters, you use that interpreters to build new interpreters. For instance, you use interpreters that are able to manage a web service connection in order to create, on top of that, new ontologies that are managing web service connections. So you don't need to go to the source code anymore. You are going to create new ontologies on top of the basic ones. Mm-hmm. In fact, this is a recursive closed subset of the world of technologies. As you know, technologies are recursive and closed world, and this is a subset that has the same properties of the technological world, but in a small size. But it can represent in a semantic way every kind of concept that you have. And its implications in terms of technologies, whether creating a specific interpreter or using an existing interpreter, creating an ontology on top of that. This is the idea. Sometimes it's really complex, because it's a world that is able to create itself. And I mean, sometimes it's difficult to move in worlds like that.
Yes, yes.
Okay, so Manu, there's still time for your question. You raised your hand.
Yes, first of all, thanks for the presentation. very interesting. I would have one question concerning the ontologies. So especially they are directly interpreted. Now, if you expect a change in the ontology, I would be interested in if you provide some kind of versioning. For instance, if you have all running instances, like in a running process, and you change the process model, are the running processes adapted, or are they still finished in the old version, or are they migrated to the new version? Do you have some ideas how, or already some support for these evolution scenarios?
Well, this is a problem that we have not solved completely yet, and we are developing now what we call Atlas, that is an ontology to store the designs of the business processes for customers or ourselves. And the idea is that we are going to have a repository of designs, and those designs eventually will become formal ontologies and systems. But what we have not solved in our ontological base today is going to be solved in that point, because what we are trying to do now is to raise to version. It's a definition in the ontology, but tracking the life cycle of every definition. So every assertion is stored, and the life cycle of the assertion, the different modification of this assertion are going to be stored, so you can track backwards every change that you have done in every assertion, and then you can freeze versions of the system, or you can clone it, creating new trunks or whatever they are known. And this is something we are going to do now. We have a lot of ideas, but it's in our ontological base today is not yet something we have a solution. But tomorrow we can speak with Pablo, because Pablo is the guy who knows more about that.
Very interesting. Thanks for the insights and for your talk.
Thank you to you.
Oh, now I see Massimo. Raise your hand, please.
Yes, hello. Well, thank you for your talk. I agree with Manuel, it was very interesting. My concern is about the real-time requirement that often is a focus of these digital twin technologies, especially when you have a digital twin of a physical device. Getting information in real time is complex and costs a lot in terms of sensors and stuff like that. So often for a lot of information where you can't put a sensor, or you don't want to put a sensor, you do some inference to understand, to try to guess what is the information that is missing at real time. So my question is, do you feel this kind of constraints also in this domain?
Oh, yes. Well, we are not using digital DTOs for industrial purposes. I mean, we are using it for organizational purposes, and usually the requirements for latency, for real-time response time are not so strong. In fact, I mean, we are working in the range of 100-200 milliseconds of average response time. If your requirements are below that, you need below, I mean, for instance, you are trading things in the United States, and you need a response time of microseconds. I mean, a digital twin is not the solution. But if you are thinking in processes where 100 milliseconds or 200 milliseconds are reasonable response time, this is a good solution.
Yes, I understand that. So you also assume that you will get all the data you need for the reasoning. So there is no need to infer some data that you cannot measure on the real world.
I don't know if I understand your question. I think it's part of the context that I have not, it's not in my mind.
Yes, so beside the real-time problem, you're right, the latency is probably not your main issue. There is this problem of getting information from the real world, right? So somebody has to insert information. For physical systems, it's the sensors. In your case, you have other ways to get this information.
Yes.
And then for physical system, where you can't put a sensor, you use some statistical inference, for instance, to get the information that you can't get directly. So do you have this kind of technology too here, like the information you cannot get, but you need to infer it statistically, or with other machine learning
yes
tools?
No, you can do that, not in the present description or I mean the reality of our digital twin, but at the end what you are describing is an ontology. You're going to describe an ontology of getting of inferring information from a data source that is incomplete, and you are going to create the concept of completeness, and you are going to create the techniques to do that within the digital twin. So maybe you need a kind of connection with a machine learning device, and this connection is going to be done using a protocol. Probably the protocol has been already included in the digital twin, so you don't need to do any other thing that designing or conceiving your ontology. Is how my system is going to work in this situation, and this is my ontology, and I'm going to apply these rules to this problem. And this is the standard technique. If you see that there is an incomplete functionality because this is the first time you approach that problem, and this is something that happens in my company every day, is that the first time we have a problem, so we extend the ontology. So we don't need to make any program. We extend the ability of the system to approach new requirements, new functional or technical requirements. And this is the ability of the digital twin to extend in an unlimited way its capabilities to cope any domain. And this is the idea of scalability of the digital twin.
Okay. So I have to watch a bit the time. So thanks again, Alfonso, for your presentation. So it's now time to move to the next speaker. Is Geza Uksar by IncQuery Labs.
Yes. Hi.
Hi. Try to share your screen.
Hello, everyone. Yes. I'll try to share the screen. I am not able yet.
Maybe Alfonso, you have to stop your sharing.
Yeah, I don't know if that's the reason or if you have to give me some. Let me see now.
Yeah. Try now, please.
Now, okay. Now I'm able to proceed.
Yes.
So now you should see my PowerPoint probably.
Yep.
And in a short while, you'll be able to see. So now you should see my title. So do you see and hear me loud and clear?
Yep, you can go ahead.
All right. So thanks for the invitation. It's a great opportunity for me to be here and to learn this and that about low-code engineering with you guys, being the experts on that. I'm not an expert on that, but as you might know, IncQuery Labs has been active in the project, also through Benedek, our PhD student. And what I'm gonna tell about today is kind of because this is an industrial session, and that's why we thought that this time we will not focus that much anymore on the, say, underlying technology and concepts, but trying to give you a kind of an overview of what our main product, the IncQuery Suite, actually does and how it works. Of course, so the talk will start very gently, I would say, giving a rather soft overview of the architecture of the tool suite and the main concepts, and of course the motivation. That's what we should start with, and that's what we are going to do. And then we will so towards the end of the project I will slide into some case studies where also some details will emerge, which might be interesting to you, I guess. So let me then just start with this kind of gentle introduction. What is the context where we are moving, very broadly speaking? What is the challenge or the challenges or the challenge complex which we see, and how do we want to go about it? So the basic observation is that if you take a look at the mostly the tool landscape, so let me just be open about it. I think it's mostly about the state-of-the-art tooling which is around in model-based systems engineering. If you look at the tool landscape, you'll pretty soon realize that somehow that kind of paradigm shift, which already happened in other contexts, like usual, conventional software engineering, that kind of paradigm shift in the tooling still did not happen, or just about to happen, in the world of model-based systems engineering. Why am I saying that? So just as everywhere, the complexity of the project is increasing. That's for sure. But still, the tools which you are using to interact with your models are pretty much still the same, also with respect to their look and feel, but also with respect to their technological baseline, is the same as, I don't know, 15 years ago, maybe. Of course, the tools are continuously updated. I'm not saying that you're dealing with 15 years old releases. I'm saying that you're dealing with 15 years old concepts. And an even bigger problem, and I think this is also something which is a very fundamental problem of semantics, and which in a sense also ties back to the problems raised in the previous talk, is that if you want to have a successful project within model-based systems engineering, then what you absolutely need is a there are many words for that. Let me just pick one: interoperability, which means that it will be essential for you that the different aspects and parts and components and whatever of your project, the different modeling layers, if you wish, are somehow interconnected and can be interpreted and analyzed as such. So this is a little bit broken down on this slide, which is, as I said, still very superficial. So we can say that there's in the state-of-the-art tool landscape of model-based systems engineering, there's no real like established solution for global consistency. So this kind of interconnected data access layer, it's difficult to customize your solutions for your own project, and then your data, or your whole enterprise might get locked into certain solutions and only able to move within that certain technological and conceptual space, which can be time and resource consuming, say the least. So this is something which we want to deal with. This slide is pretty much full with information. So this is how we summarize those features and concepts through which the IncQuery Suite aims at proposing or providing a solution to at least a part, or at least be at the front of facing these challenges. So the IncQuery Suite, I'll tell you this and that about the architecture and the overall structure later. But this is a slide of what you actually get as features. So as I said, I will be pretty much zooming in, and this is still a kind of an overview. So of course, the IncQuery Suite, as I said, even though it has a kind of a novel infrastructural and architecture concept, it's still tied in the systems engineering world, and this with a purpose. So of course, one of the main use cases, which you see on the right, is to validate your engineering process, but with particular focus on SysML as a language. And of course, what that validation could mean in reality, I think we all know, we all have use cases for that. So I'm not gonna delve into that right now. Also, of course, it's getting more and more important that those kind of analysis scenarios which you run over our models get somehow interpretable for a broader audience as well. That's why there is an additional kind of, nowadays you would call it a dashboard. So there's a dashboard component or just some visualization. Yeah, I'll get into the technical side of this later. And that's what's also interesting is that, of course, interacting with your models. There, you also need to come up with some means. The point here is that we aim at an efficient and effective combination of different kind of information retrieval languages, or as they are, most often called in our community query languages. So we have like different indexes to access our models, and therefore also different kind of query languages to interact with them. That's also something which I'll get into soon. And of course, this is kind of not necessarily a distinct feature on its own, but this kind of thinking kind of accumulates in an integration platform. So from all this emerges kind of the vision of an integrated tooling, integrated combination of different toolings and technologies, which you can customize for your needs, but which is still fully integrated and globally accessible and globally consistent throughout the whole project. So this is just, yeah, in case you're interested, I'll not go through these. This is just if you might have questions on what are these technologies which we try to combine together. We've been trying to, of course, this is in constant development, so there are more. This is, I just left this slide here in case you're more like technologically interested, then you can check if your technological space is already included here. Of course, there are future plans for many other things to get connected. But let me just start going into the drifting into the more technical part of this. So this is what because this is called IncQuery Suite, and I already said it's a tool suite. So you might ask yourselves, what are the components then? Why is it a suite? Or how should I, think about this as an actual tool? And the answer is, at least the first approximation to the answer is this. These are the basic components, without seeing much from their internals. So I would say that the heart of it, that's why we are going to take a closer look to it, is the so-called IncQuery server. So this is the component which will connect to these singular data silos. This is how we call these, these separated technological spaces, usually tied to a single tool as a mode of interaction. So this is where you can use a connector to connect to a silo and extract data from it. And this, I mean, given according to your project needs, you're then combining the data, and you have then kind of a unified knowledge graph, if you wish. And of course, the IncQuery server also provides it to you in a server-based manner. That's the whole point of it, and that's why it's called the IncQuery server. So there's a lot of cloud and other repository-based technology behind, in order to provide you with easy access, easy web-based access. Still, there's, partly historically, but also conceptually, of course, it's not bad to have a desktop counterpart of it. This is where the whole story started, actually, the IncQuery desktop, and this is still a very useful and very widely used tool. Therefore, it's still part of it. This is a SysML focused add-on. This is particularly for the no magic ecosystem. So if you know Magic Draw, which is probably the most widely used systems engineering tool, this is an add-on for that, providing some desktop features for SysML, because this is still, I mean, we are talking industrial, right? So in the industry, it's still very important to also provide, to be able to provide solutions for typical use cases, which in large enterprises in particular tend to stay around for a longer while. Therefore, it's important to also have such a component. Notice, however, that everything available in the IncQuery desktop is also available in the IncQuery server. Maybe not that easily, or you have to learn the way to use it in order to adapt your, let's say, desktop-based application scenarios into a server context, but that's absolutely doable. So functionally, this kind of covers the whole story. And then there are these are kind of the user end features, the model viewer and the model analyzer. I will not probably give you a glimpse of that if we'll have time. These are not that much in the focus today, but these are just web-based applications. So this pretty much running your browser, and these provide different interfaces to, as the name actually says, to actually take a look at certain parts of your models which you have filtered accordingly, or to analyze. Which more or less means query, and then if you want, visualize the results of your querying. And of course, these can be complex querying scenarios, not just single queries fired through IncQuery server. So these are the components, and this is how I think I have almost said pretty much what I had to say about this guy, but this is just, we are getting closer and closer. I wanted to be a bit more precise on that. So yeah, I've already told you there's the IncQuery desktop, which is on the desktop authoring tool side, and then there can be many different repositories which can act here in the middle. This would typically be like model repositories. So the most typical examples for this kind of backend behind an IncQuery Suite scenario would be either the built-in solution of No Magic, which is in Magic Draw, or the Cameo Systems Modeler, which is called Teamwork Cloud, or this would be MMS from the OpenMB suite or initiative. I'm pretty sure that you're familiar with that, but of course, if you're not, just feel free to ask later, or maybe even right now if you want. I don't mind taking questions as we go. So there is a repository in the middle, some kind of a backend, and this connects to. So this is where the IncQuery server takes its data. This is this kind of a middleware layer in between. Taking care of data uniformity. And then this is what I actually said I will give you more details on that, on those user interfaces. So there is a backend repository, then there is the IncQuery server as a, let's just, for the sake of simplification, let's say it's a middleware, and then there are different ways of interacting with it. I've already mentioned that there are some custom browser tools. Then there's also a web console. The good thing is that we are relying on the open API technology, which will mean that you can integrate pretty easily with any kind of other cloud-based or REST-based services on the internet. And then, which recently has become a very important medium of interaction with the IncQuery server as a whole, and which proved to be a very useful tool for project-specific customization, is the Jupyter ecosystem or Jupyter notebooks. I'm pretty sure you've heard about them. I think we might see also a specimen of this towards the end. So this is also a very important way of interaction. So you can just, we have prefab examples. You can open up your own notebook and you can interact with the IncQuery server and yeah, fire queries to it. Also, yeah, have prefab dashboards. Of course, if you know Python, you can code your own dashboards. Everything is possible, whatever is provided with Jupyter. You can make great use of it in this context. But you might, at this point, already have become a bit curious what's under the hood in this IncQuery server. How does this actually work? So let me just try to give you, without becoming too technical, let me just try to give you an architectural overview, but a bit closer zoom this time. So if you remember, if you still remember what I've just shown in the previous slide, on the left hand side of this picture, there are the different modes of interaction, let's say. And in any case, once you've entered the internals of IncQuery server itself as a tool, everything is quite uniform in the sense that there is a, of course, the actual data structure or the actual internet structure is not as simple as this, but you can easily understand this via this depiction. So the overall architecture is that there are connectors which discover and then acquire the data from different data sources. These data sources are depicted here with this engineering repository box on the right. Of course, it's very convenient to fetch that data via some kind of open API interface, because this will make the interface reusable. And of course, any serious tool provides something like that, or if not, then that's probably the easiest way to interact with any legacy system as well. So you're fetching the data. That this was this kind of discovery and acquisition phase. Over in the cloud, over the discovery, you see that there can be list of project commits, revisions. Yes, this is something which we also take into account because we're talking about repositories, so there might be a kind of a version and concept behind, and this is also taken into account. And then it all goes into the index. And yes, I mean, no, let me just stick here for a while, just to notice or to let you notice that the index is mostly a persistent index here. So this is very useful if you have a long span project to have things persistently indexed. And this is typically something in the cloud. So this is again to emphasize to foster flexibility and reusability even more. This is why we want to rely on cloud-based technology as much as we can. So another aspect of this is not very different from what I've shown, but this is not the infrastructure perspective anymore. But in the following few slides, I would want to give you some examples on how you're actually interacting with the data which you have fetched, as seen in the previous slide. So there are three main query services which we provide, which are completely built in, and which for which you actually have, if you're not a programmer, you can even go about, yeah, we are talking about low code, right? So these are the parts which are pretty much low code. you only have to know the query language. Of course, that's still a requirement. You cannot. I'm not sure how we could come around that. But once you know the query language, you have built-in interfaces to fire queries and therefore to retrieve information from this global digital thread, as we call it. So this combined engineering data repository, which you have acquired. And this is the first. I want to show the three main modes of interaction here. The first one is, it's called VQL. It's the wired query language. I think you might. So if you're in the project, I think there have been earlier talks which have been introducing Viatra as a technology and maybe also the query language. So I don't want to spend too much time on that. I just want to show you that this is that kind of interaction with the model, which is in the typical vein of model analysis and transformation as known in the world of model-driven engineering. So this is the classical school. This is actually built on top of the Eclipse modeling framework, EMF. So the language itself. And Viatra as a tool is still within the Eclipse environment. Here you are not tied to the Eclipse environment anymore in any sense. Still, that's where the language originates. And this would be a typical model querying language in the usual sense, the VQL, the Viatra query language. And yeah, what you see in the bottom of the picture is just that you have the persistent index, but of course, once you want to interact with it, once you're actually firing a query, let's say this. So this is an example query here, identifying which elements are fulfilled by requirement, consisting of 3 not very complicated clauses. So I think it's quite readable, which is also, yeah, was one of the design goals of the language. So whatever you want to query, you're loading it into an in-memory index, and then you're good to go. You can fire your query. But there are some other alternatives, and for those other alternatives, there are other backend solutions or background solutions for you to help with. Again, we are relying on a cloud service, the very famous Elasticsearch, to also provide the user with a full text search capacity. So full text search just means that you don't have to rely on a structured query language. That's how I typically call it. You can just, if you know some syntax, but the syntax is of course much more lightweight than in the case of any structured query language. If you know some syntax, then you will be able to fire full text search queries towards your database as well. And then there's a third alternative, which is in some cases, as I know it from experience, can be very useful. Of course, we are in the world of model-based systems engineering, but this concept which we are having here has a very holistic view on it. Therefore, of course, technological spaces like that of ontologies or other kinds of graph databases, if you wish, or triple stores and things like that, are also can be very relevant. They are not necessarily, but there can be many projects where this is relevant. Therefore, the IncQuery server also supports SPARQL querying in particular, which is, I think you'll agree with me, is pretty much the de facto standard way to interact with such triplet-based engineering information. And again, we are relying on the widespread and actually very useful cloud-based technology. In this case, so to make this happen, I mean SPARQL querying, we are relying on Amazon technology. In particular, Amazon has a graph database or triple store called Amazon Neptune, which is yeah, within the the Amazon Web Services space, absolutely cloud-based, and this is where you fire your query against when you want to rely on the Spark capacity of IncQuery server. There's an important note here. Given that there is a uniform data layer behind, this does not mean that, for example, if you're using SparkQL, you're only able to reach and query and interpret that parts of your data which are natively in that linguistic or data structural context. Once you have loaded the data appropriately within your own IncQuery server setup, you will be able to reach any kind of the data by any of these means which I've just listed. And if you do some programming, then also some other means are easily accessible. But I just wanted to focus on the main things. Yeah, as I've told you in the end, I've brought with me also some case studies, some industrial, just to underline the industrial relevance and usability of such a solution. And then I'll also, if I still have time, bring you some more research-focused case studies, so to say, or these are rather just research goals we are pursuing. But let me just briefly then first show what kind of, in what kind of industrial context can something like the IncQuery Suite be useful. And one of the main examples is our work with NASA JPL. So NASA JPL, the Jet Propulsion Laboratory, is one of the earliest adopters of model-based technology. And when it comes to industrial applications, they are still among the leaders, if not the leaders in the field. When it comes to conceptual development, etc., and rather complex tooling and conceptual environment behind all their model-based engineering efforts are called CAE, computer-aided engineering, and this is the platform which IncQuery Suite is also a part of. So this is a rather long slide on what you can actually do with the IncQuery Suite within the computer-aided engineering environment of NASA JPL. So there's OpenMBE involved, of course. They are mostly using it for validation. So of course, this is a very typical use case here. But then there are also like other goals pursued here, which we can also be of help with, like requirements analysis, etc., etc. And this the Jupyter Notebook based backend is also, this has been tested first in NASA's environment, and this is still an important way of interaction for them with their models, made available by the IncQuery Suite. Another interesting partner was, this is again rather just to show what kind of challenges arise in the industry around such solutions, and how can we proceed about them. This is a collaboration with the kind of the innovation spin-off of Airbus called A-Cubed. This was also a project involving many typical tools and their integration. I think I will rather just switch here and show you what actually happened, because yeah, time started to run out and there's still a couple of interesting things I wanted to show you. So at A-Cubed, they have built a 5-layered conceptual frameworks. This was kind of the basis for all the modeling, kind of a holistic modeling approach here, in a layered manner. These were the layers which you see on the right, defined by them. And then the actual tooling challenge, I think there's something very important and interesting about it. So at the end of the day, even if your interoperability platform is absolutely super modern and uses all the newest technologies in the background, that's all cool, because that's where you want to be and that's where we should be. But sometimes there occur scenarios which you still have to prove flexible enough to understand, to give support for something as old-fashioned as Excel. So Microsoft Excel is still the most widely used engineering tool in the whole world, and this is this doesn't even have any serious contenders. This is just a fact. And this was in particular a project where you had different aspects of this layered modeling space, which I've just shown. Some of them modeled using the already mentioned Cameo systems modeler. Then there were some Simulink models also in the place, so that's why the MathWorks logo is here. So MATLAB Simulink was also in the, and this is great for IncQuery server. This is a very typical scenario. You have different but interconnected modeling spaces, and then you combine them in a single interoperative platform. And then in this case, we also had to, because this was a requirement, we also had to communicate with Microsoft Excel to produce some reports in the and other forms of dashboards within that environment. And this is how it went, actually, if you have wondered. So this is also useful to see, because this is a typical usage workflow. You edit your system model in whatever tool you want, then you commit the changes to repository. In this case, this is the built-in solution for Cameo. It's called Teamwork Cloud. And then within the IncQuery server, you are, I think by now you can imagine that, build up a kind of a simulation integration loop, also involving MATLAB Simulink as well. And then from that interoperable data existing and being uniform within IncQuery server, you're able to, with another connector, you're able to create your generator, which will provide the reports and all the other stuff which is necessary on the web, or in this case also in Excel format. Just very briefly at the end, some kind of research, more research-centered case studies as well. So as we go about with this, of course, so we have our background is originally in like classical academia, in research, and this, even though our activities kind of evolved into this kind of classical development or tool, we want to become like a tool provider for the whole community model-based systems engineering. This all involves a lot of research. I mean, continuously trying to answer some research questions as well. And one of the central questions, which I think you have already heard quite a number of times from Benedek, is that we want to, so using the IncQuery server technology as kind of an enabler technology, we also want to provide model checking services within this environment. So I think you all know very well why it's very important to, when we are talking about validation and verification of models, why it's important to not just stick with the syntactic or structural level, but go behind and trying to analyze the dynamics of the model, or the actual behavior of what's modeled there. So this is just an example which do not really want to delve into. This is about a battery. One of the modules. So this is here the important message, just that you can even have like parallelity in your model. So of course these are the actually interesting examples within model checking. So here one part of the of this model, of this behavioral model, is about data transfer. while the other controls the batteries. And you can formulate a goal like you should never transmit, I mean, never perform this data transfer task in the upper, I mean, depicted here in the upper part, if you do not meet these requirements or these constraints, which actually mean that you should never transmit when the battery is below 40%. And again, this is just might be instructive to see how you are actually building it up using the IncQuery server technology. So again, on the left-hand side, you have some SysML tool. You can upload your underlying models, which you're performing validation on, into a model repository. And here in this case, there are some further steps compared to the scenario which we have seen before, because in this case, of course, you would also want to rely on some formal models and translations for your structural behavior models to become like a bit alive, at least for our interpreter. And this is what's seen in the upper right of the picture with that additional steps and with that intermediate models, sorry, coming from the Gamma tooling environment, which is an Eclipse-based, a very nice state chart solution. And also, let me just note that there's this is kind of bidirectional, which is also, I think, very interesting and might be nice to see, is that you're also able, so once you have obtained, so here in this scenario, we're using Upal as a model checker. Once you have obtained your model checker trace, you can kind of bring it back, the results into this intermediate Gamma, so the state chart representations. You can annotate them, and then those back annotations can even further propagate it back, which means that at the end of the day, you might have a SysML sequence diagram which is annotated with the results of the actual model checking, which is, I think, the real power of it, at least in my eyes. Okay, let me see if I still have.
You are almost running out of time. If you want
all right.
Yeah, so please come to the conclusion. So we have a few minutes for questions.
All right, then.
Okay,
then we skip the last example. Unfortunately, at some point, if you're interested, I'll be able to show you that. So I think we can then just, if we still have a few minutes at least, I thank you for listening to me, for having me here, and I think questions are the most important part of any conference or workshop. So I would be happy to take some if you have any.
Yeah. So thanks for your interesting talk. So yeah, we are close to the break, but yeah, if you have questions, please raise your hand and feel free to stay a few minutes more than planned from the agenda, so that we can ask questions to Geza. Yes, Iriam, please.
Hello. So thank you very much for your presentation, Geza. Actually, my question is a bit more specific. I'm referring to the slide where you explained a bit about the repository under the hood, and you mentioned, you deposited there a Sparkle query, and you mentioned that you can query different models by using Sparkle, even if they are not triples there.
Mm-hmm.
So the original format of the model you have persisted there. So I'm wondering, how is it managed? So are you converting any kind of models into some triple format, or how is it managed there?
Yes, so essentially, yes, this is a very good question, and this is why I mentioned it. I think this is an important aspect of this. Indeed, there is a so-called compartment format. So everything, whatever comes in on engineering data, gets into into these uniformized compartments. And the underlying observation is that obviously the triple semantics, while it is also a technological means in the semantic web technological space, of course, generally speaking, this is the underlying semantics of any graph models. So that's why we found that it's possible to communicate with any kind of models. I mean, regardless the original format, we're able to communicate with those parts of the engineering data using SPARQL as well, because we have an intermediate common representation which understands this triplet based thinking.
Understood. Thank you.
Thanks.
Okay, so thanks. If you have any other question, or let's say it's now time for the break. So, but if you can stay with us, and then let us know. I mean, at the end there is a group up session. If then anybody want to ask you a further question, you can stay here, or we will send you questions we receive by email.
All right, that's very kind from you. I don't know. I'll try to listen to as much as I can from this very nice workshop, because this is a great program. But yeah, if I'm not around, then you can just forward the questions to me. And thanks again. Thanks a lot.
You're welcome. Okay, so thanks, and it's now time for a short break. We will restart around 11 with the data trees. So thanks for joining, and talk to you soon. Hi, Jürgen. Welcome.
Hi,
We
Luca.
are going to restart. Just wait 1 minute more. Okay, it's 11. I think that we can restart. So the next talk will be done by Jürgen, by Diana Trace. So Jürgen, stage is yours. Please introduce yourself and your talk.
Cool, thank you. Let me just also find my slides. I have a couple of slides prepared. They are somewhere hidden behind my windows here. Share screen and just, this should be fine. Okay, perfect. So please let me know if the screen size is not fine, then I can also move to another screen and adjust the size a little bit.
Well, let's say I still see a few black on both sides, but it works, let's say.
Okay. I can, as you wish. If I should go for a smaller screen, then I just switch. Let me just rearrange real quick.
For me, let's try.
Because it's let me just move it over here and try it again.
Now it's
okay, and that should hopefully do the trick.
Yeah, now it's bigger.
It's okay, perfect. Let's go with this one. And I will just try to also arrange my windows here. Cool. Perfect. Yeah. Thanks for the invitation and also thanks for the introduction. Today, I want to share a little bit about an open source project that we at Dynatrace are working on, and it's part of the basically of the Linux Foundation or the Cloud Native Computing Foundation. And I think it fits also in this kind of workshop here, although it's not really model driven. I've just had a look at the agenda, and I think it's really based also on model driven engineering. So in Keptn, it's not really model driven engineering, but what we're also following is the approach of more of a declarative description of let's say sequences, workflows, processes, however you want to call it, and not so much on directly programming something, but more describing it and then having some kind of automation in the background doing this. So the talk is called Modern Continuous Delivery with Keptn, because this is what the Keptn tool is basically doing. And I might take around 30 minutes for the presentation, and then I'm also happy to discuss how Keptn might fit into other ecosystems, or what we learned also when we have been building Keptn, which is now around for around 2 years, I would say. If you're interested in the project, you will find a lot of links also here in the slide deck, and I can also share the slides later on if you're interested. So just as a quick introduction for myself. So my name is Jürgen. As you've already seen on the first slide, I know a couple of you. I just saw the people that also joined this meeting, and I know a couple of you because I also had the opportunity and the chance to work with some of you during my studies. I did my studies at the JKU in Linz, and also we during this time we had a joint project with the BIG from the Technical University of Vienna. I worked together with Manuel Wimmer. Luca I also know because he's now based in Linz, but I did a Marietta Blau scholarship at the University of L'Aquila, and I think it's the alma mater, so to say, of Luca or also. So I know a couple of you, and it's great to be back kind of in this community. After my time at university, then I switched to more towards the industry, and I now work as a technology strategist at Dynatrace in the Dynatrace Innovation Lab, and in like the more or less from the beginning, I was involved a lot into open source projects, and also the project I'm talking about today is also open source. So why am I actually talking about this project, and what are the problems we want to solve? When we, as an organization, as a company, at Dynatrace, when we are talking to our customers or partners that are also using the Dynatrace software, we have a lot of conversations on the way how they are delivering the software to their end users, like how they are building their pipelines to roll out the software from, let's say, a developer all the way to production. And what we've learned when we talk to customers and partners is that they have quite large pipelines, and the problem is that those pipelines, they break, as a lot of other software is constantly breaking, and we need to fix this. The same is true with delivery pipelines. And this quote comes from Christian. He's based in Germany, and he's one of those senior DevOps engineers, pipeline engineers, and they have a pipeline for the delivery of their software, and it's not the software itself, it's just the delivery part of the software, and this pipeline is more than 1,000 lines of code. So it's a fairly complex delivery pipeline, and if there's something breaking in this pipeline, they need to find the bug and they need to fix it. And it's not, with pipelines, not the same as with usual software that you can easily debug it and you have test cases for it. But this is really a cumbersome task, as you can also see here. What are parts of the commands that are executed? Sometimes it's really low level, like executing a curl or unzip directly from the command line. So it's really low level code, and if there is an error, it's really difficult to fix. So what a lot of organizations are doing, and also we made this, let's say, mistake, or we followed this pattern, is that we have a working pipeline to deliver our application to our end users. And if it's working, we use it, and we use it again, and we use it again, and it's more or less a copy and paste of our applications. So we might want to start with one microservice. We have one pipeline. We come up with more microservices because we want to build a whole application. We are working on a whole project. So we are building more and more pipelines to deliver the software, and coming up with more and more pipelines. And if the pipeline is working, we might just copy and paste it because it works for one project, why it shouldn't for the other project. But then are more teams inside of Dynatrace. We have a lot of different development teams that need to deliver the software. So it's a lot of copy and paste, and we call it kind of a snowflake environment. So we have a lot of different projects that are using maybe the same pipeline, and as long as everything's running fine and there is no issue, it's also no problem. But if you think of a bug fix, if you think of an update of a tool, you have to switch to a new version of a tool. Maybe there is some dependency with the security vulnerability, and you have to update this dependency. You have to touch all of those different pipelines, and this makes it really difficult. And another problem that we're seeing is that a lot of organizations, so this is a quote from a company based in Vienna, run by Roman Ferstel, and what their actual problem is that they have to kind of reinvent the wheel for each of their customers. I'm not sure if like in this workshop, if terms like SRE and SLOs and if everything is already familiar, I don't want to focus here on this slide on these technology terms, but what I just want to focus on here is that for some companies, they spend a lot of time on manual work to create some scripts, to configure other systems, to analyze some test results. They are doing performance tests on the software, and they are doing a lot of also this maintenance code. A lot of the code, they have to rewrite it again. Maybe they copy it from somewhere, but it's not code that is already generated for them. They have to rewrite the code for each of the projects, and it just takes a lot of time for each new project to come up with all these manual tasks and all this manual code. So what we have introduced around 2 years ago is an open source project called Keptn. And the idea of Keptn is that it is a kind of a control plane where you can connect your different tools, and the heavy lifting and some part of the code generation, this is done by Keptn. So you do not define everything in one large delivery pipeline, but you would just define the process and you would connect the tools. So you have a nice separation of concerns, and basically the tool specific code goes in combination with the tool, and the process definition goes into Keptn. And with this, you can have you can benefit by reducing the complexity and also reducing all the lines of code you have to write, which I will show just in a second. So basically, with Keptn, you have it running. You, let's say, pick your use case. You can do a couple of different things. As the three problems that I've briefly discussed, they are from different nature. So it's not that Keptn can only do one thing, but it's really what you want to do. You will just bring the configuration, and Keptn will do the automation behind the scenes. So you will bring the configuration, like a process definition, also quality description that the service has to satisfy, like a specific response time or a very low failure rate, or some maybe CPU consumption. Maybe it's not allowed to consume more CPU than some specific threshold. And then you can connect to different tools. Those tools might be like Jenkins, which is a very well-known tool for CI and CD. Then tools like GitLab or GitHub Actions, maybe other tools like performance testing tools such as JMeter, Locust, Artillery, other tools for deployment like Helm, like Argo CD, if you're more talking in a cloud native environment. So all these different tools, you will connect it to Keptn, and Keptn will then orchestrate these tools. How does it do the whole orchestration? It's based on a standard on cloud events, and one cloud event will have all the information that's needed for the tool to actually execute the job, and the whole job execution of the tool. Everything the tool has to do is then very close to the tool and not part of the process definition. And I think I have an example also later in the slides to make it more concrete. So what are then concrete examples? How can Keptn help large organizations to accelerate their innovation and to deliver the software with a higher frequency and also with a higher quality? So we've worked together with Sumit. He is an engineer at Intuit. Intuit is a very, very large financial institution based in the US. And I think more or less everyone that has to do taxes in the US knows about Intuit or some product of Intuit. And what they are doing, they are in their tool stack, they have delivery, performance testing, and also the CI part of the pipelines. And they are doing continuous evaluations of the quality of the software by executing first performance and load tests against the software, and then evaluating the quality of the software with Keptn based on service level objectives. So this is just one way to define the quality criteria of the software with service level objectives. And Intuit, very large organizations, they are running multiple quality evaluations in their pipelines for their software. For Triscon, they were able to scale the number of performance tests they are developing together with the customers, and also the number of tested apps based on by using Keptn and the concepts that Keptn provides. And for ERT, they scaled their the whole platform team. They scaled the number of applications, and also they scaled the number of stages. If you think of large institutions, they might not deliver their software directly from the laptop, from the developer to production, but it goes through different stages, like a pre-production, a QA, a hardening, a testing stage. So all these different stages, they have to be kind of connected, and usually there is a quality check once it moves from a pre-production environment to a production environment, and all of this has also been automated by Keptn. And then just recently, we also talked to a large financial institution based in Austria and very well known, I think, in Europe. It's Raiffeisen. Raiffeisen Software is the company behind the Raiffeisen Bank, and the Raiffeisen Software is writing the mobile banking application, and they are also doing, before a new release of the mobile banking application, they are checking the quality with Keptn. And they are doing this by just defining a process definition, how they want to check the quality, and all the heavy lifting, again, is taken care of Keptn behind the scenes. So I would just go into one slide where I think I can explain it best how we are doing this. So let's probably start here. So how can you basically allow Keptn to do the heavy lifting and to separate the process from the tooling? And on the left-hand side here on this slide, we have some basic building blocks for a CI and CD pipeline. Usually, first you build your software with let's say the outcome of the build would be a container image, like a Docker image, so to say. There might run already some unit tests as part of the building process. Then you might prepare your environment that we're able to deploy this new Docker image into this environment. Then the environment or the Docker image gets deployed. Then we want to run some tests like performance tests. And after the test, we want to notify maybe the development team or the testing team about the test results. And we want to evaluate automatically the test results. And if everything is fine, we want to promote it to the next stage. We want to ship it maybe to production, or we want to roll it back to the previous version so that we never break anything in production. That's really one of the most important parts here. But these are like all the different building blocks of the process. There are a lot of different tools that are connected to the process. Like we need a deployment tool, we need a monitoring tool to collect the test data or to collect the performance data during the tests. We need to connect a test tool. So we could do this directly inside the pipelines, coming up with or ending up with 1,000 lines of code that we saw earlier in the example. Or we could do a separation here by basically introducing an intermediate layer. And with this, what we have introduced is some kind of eventing layer based on cloud events. There's just one specific implementation of eventing or of a standard how to define an event. And we are using cloud events here. And with this allows us to separate the process, and I think I have it here, which events to generate. Everything goes here into the process definition, and the tools, they actually we define here who is consuming this event. So let's say if we send a test event, then the test tools would be interesting in this, and they can just execute upon the test events. But thinking about some notification tools like Slack, Microsoft Teams, WebEx, or whatever tools you might have, they might also be interested in some kind of some process steps along the way, such as a finished deployment. If I'm a developer, I might be interested, okay, if the deployment is finished, if my microservice is now available in the pre-production stage, that would be very valuable for me, because then I can test it, then I can have a look, and I can get this information directly via Slack. So I do not have to change the process definition. I just connect new tools via cloud events to the process, and then I get notified directly. So with this, what we could achieve, especially at ERT, was to reduce the number of lines in their pipeline code from more than, what is it here, 1,000 lines of code in their pipeline to around 72, or let's say it's 80 lines of code, by still keeping the same functionality. So the thing here is that it's basically this is possible by first introducing this eventing mechanism, and it's sometimes a little bit shifting the code from the pipeline itself into the tool integrations, and a lot of the automation is also now part of Keptn itself. So it's based on the best practices, and it really allows to to follow the process without reinventing basically the same tool integrations or reinventing the same quality checks over and over again, because this is now based on declarative information. So how can we build a declarative description for a quality check? And I think I have it in the next slide. So here I was just I'm just highlighting how we can define the process in Keptn with only defining the process without defining the tools. Again, the process and the environment definition is here. It's the declarative description. You can also do this in JSON. In this case, it's a YAML format, and it's just defined here for one specific stage. I called it def, and one delivery sequence consisting of different tasks is defined here. So first we want to do some deployment with a couple of different properties that are important then for the tool integrations. We want to execute some tests again by passing some properties, and there might be more tasks that we want to execute as part of this delivery sequence. And I've just added here a couple of different logos so that we can think about what are the typical tool integrations that you want to add for some specific task. Like for deployment, typically you want to add some deployment tests, deployment tools. For tests, there is the big ones and traditional ones like JMeter or BlazeMeter or NeoLoad, but you might also use chaos engineering, chaos testing as part of this phase. Again, the important part is it's a separation of the concerns, and it's separation between the tooling and the process. So in the shipyard, we only define the process, and then we connect the tooling to the process. Okay, so one important part is also how can we check the quality of the software. As we see here, there's one specific task which is called evaluation, and during the evaluation we actually want to check automatically quality criteria of our software. Quality criteria actually at runtime. So not so much quality criteria on the number of lines of code or quality criteria on how many functions I have or how often a function is called, but really quality criteria during runtime, such as memory consumption, response time. That's a very important criteria for most of our customers. Error rate, obviously, we want to detect if there are any exceptions coming up during the execution of the software. So these the kind of metrics we want to check. And what we are using here is concepts from the site reliability engineering discipline. And that's heavily influenced by Google. And there are books by Google on this topic. And we are basically taking this concept and putting this into code and defining a specific format, how to write some service level objectives, and then combining this with service level indicators. An indicator is basically the metric. The objective is then some specific threshold for this metric for a given time frame. And then you could also combine this with business objectives and business agreements, but we can neglect this for the moment. So as an example, how we can write service level objectives, we can just define a list of different indicators. So first we start with the indicators, because this really gives us the value for a metric. Let's say the value for a response time. What I have here for using here Prometheus, which is a prominent open source observability and monitoring tool. So I could just define the probe duration in milliseconds. That's basically how long it takes to scrape one metric from a microservice. And the idea here is to just have a list of indicators by mapping the name of the indicator that can be reused later on to how can we retrieve this indicator. So that's basically in this case, it's a Prometheus metric written in the Prometheus metrics query language, or it can also be an API call if you're using other tools. So this is just how this metric or how this indicator is actually queried. And then in our SLO file, we can reuse this. Why did we make a separation between the indicators and the objectives? Because a lot of different organizations, or a lot of organizations, they are using different monitoring and observability tools for different stages. They might use Dynatrace in production, but maybe in their pre-production environments, they are using Prometheus, or they're using even a mixture of different tools. And again, by giving them the possibility to abstract in their objective file where the data is coming from and just connecting it to their service level indicator provider, this gives them the flexibility to reuse the quality gates also between different tools. So we can define in the objectives, we can define specific objectives for our service level indicators. So in this case, for example, we assume or we expect that the success percentage for probes is higher than 95%. Then this quality gate or this one objective would be satisfied. We would get full score on this. If we cannot satisfy this criteria, Keptn would automatically check for if there is a warning criteria, which basically gives you half the points on this quality gate evaluation, and we would still get half the points if we are below 95, but still higher than 90%. And if we're below the 90%, we would get 0 points, and we would consider this one as a low to be failed. And you can have a long list of SLOs. You can even have a mixture of absolute thresholds and relative thresholds. Relative thresholds are very, very nice, especially in the beginning. If you don't know yet your objectives, like again, I'm taking the example of a response time. If you don't know what is the expected response time of a microservice? Does it respond within 200 milliseconds? Does it respond within 50 milliseconds? You could just define relative thresholds and say, okay, it's fine if the new version of the microservice is within the boundaries of increase and decrease within plus minus 10%, for example. So you can basically write the quality check that the quality has to stay the same between the different runs, or it's only allowed to improve but not allowed to decrease, or maybe it's even not allowed to improve by more than 50%, because that would maybe already point a little bit to a bug in the software. If like the performance increase is now more than 50%, that's a little bit suspicious. So this is how you can write the quality gates. And then the heavy lifting behind the scenes, where you don't need to write all the specific code, how to reach out to the data provider, how to query the data, how to score the data, how to come up with a total score. This is then done by Keptn. And it can be used with the Keptn CLI, it can be used with the API. But what it's done is that Keptn will reach out to all the different data providers, will first individually reach out to retrieve the SLIs, will then score them, and will come up with a total score. And based on the total score, it will give you, let's say, a thumbs up or a thumbs down if the software is ready to be promoted into production or not. And actually, this picture sums it up quite well, I think. If you're thinking now about the example I've talked about earlier, like Raiffeisen software, they are having a list of, I think, 50 or more quality criteria they need to check for each new release of Mein Elba, of the mobile application. And they are doing this by just defining an objective file and defining the indicators file. They don't need to know how to query all the data for all the different microservices. They don't need to know the exact time frame when they want to query the data, because everything is orchestrated here by Keptn, and Keptn knows how long tests have been running, and then it will query the data for the exact time frame of the tests. It will query only the data that has been actually affected by the test run. So if you're thinking about a larger test environment where there might be different test runs at the same time, you only want to query the data that you have created, and you don't want to query all the noise that might have been created by other tools. And all this heavy lifting, so to say, is done by Keptn. So how does it usually look in a full process? When our users, when they are using Keptn, they typically have more than one stage where they deploy some software. So, but the process, what they are doing in one stage, this is more or less the same for each stage. So it's deploying, testing, evaluating, and then releasing. And this is exactly what we've sketched here. So it's a deploying, testing, evaluating, and then releasing by automatically promoting or by asking for human approval. Human approval is sometimes needed, especially when we're thinking about going into production. Even if all the quality checks are green, you might still want to wait for human approval. Maybe because you want to decide on the exact time frame when you want to deploy, or there are some other, let's say, business decisions around the delivery of the software. For example, again, the Raiffeisen, they deliver, or they are building software for, I think, for 8 different subsidiaries of the bank. So in Austria, we have 9 states, so to say, in Austria, and each state is its own, the bank in each state is its own legal entity, and they have to accept the new build of the software. So they cannot really auto-promote it into production for all these 9 subsidiaries, but they need manual approval. But before the manual approval, they need all the lights to be green. So they are basically having a mixture of they have assisted approval, so to say, because they need, or they are using the Keptn quality gates to check this. I now have more detailed slides how this data-driven automation can also be done, but I think I've already used more or less 30 minutes. So I would actually open up here for discussion. I think that the most important part, what I've shown, is how to automate quality checks with Keptn, and how to automate the process orchestration with the Keptn shipyard file, and then combining different tools to Keptn. I can show you Keptn live. I can show you a little bit more of what Keptn is, but I'm also open to any questions regarding the project, how you might be able to connect it to your discipline, or maybe even to your tools.
Okay, so thanks, Jürgen, for the really nice presentation. So please, yeah. So Benedict, you are the first one.
Thank you for the interesting presentation of Keptn. I have tried and experimented with Keptn already, and I have seen that it has 5 meta models. So it has the shipyard, the SLI, SLO, the cloud events, and one more that I cannot recall now. But the question would be that, do you have a meta model for the tools, actually, to describe the tools, and then how they are connected to the cloud events, to what events they are subscribed for? So do you have a JSON schema for that also, or are you planning to add something like that? So
I just opened this up in the background. I think I'm still sharing my screen, so you should be able to see this. Yeah, so it's great that you already had a look at Keptn, and exactly you already said it perfectly correct, that we do have all these different, we call it like a specification of Keptn. We can think of this as a meta model for the different types of events, like our cloud events or the shipyard file. What we do not have is a specific meta model for the tool integration, because the tool integration is actually mostly interested in the cloud events part. The tool itself needs to understand a cloud event, or the tool integration needs to understand a cloud event, and then translating this cloud event into the tool specific way of handling this event. For example, when you want to integrate a testing tool, the testing tool might be executed with a binary. So there is a JMeter that you can just run with JMeter on your local machine or anywhere in the cloud, but it's a JMeter binary that you execute, and it needs the host, it needs some test data, and what in the test cloud event itself, what you will receive is the URL where you want to send your test data to. What you also receive is the test strategy, and the tool integrations, they are mostly interested in this specification, so that they are able to parse this specification and then use the data that is relevant for them. So this is basically the meta model for tool integrations. They mostly are interested in our meta model for cloud events.
Yes, I understand this point. The question would rather be from the design time perspective, so that when the DevOps engineer is designing the pipeline and also the integration between the tools, and it might be useful to have it also as a model or as a definition. And then on the code level or on the runtime level, yes, of course. It is too specific how they react to the cloud events. I completely agree with that. But my question would rather be from the design time and from the static analysis perspective.
So there is a schema also for this, and it's also part of the cloud events specification here. So we do have this JSON schema. From the design time perspective, what we are also offering is different libraries and SDKs, not fully fledged SDKs, but it goes into the direction of an SDK, and then different libraries that already give you the benefit of code completion or some easy ways to retrieve resources from Keptn, where you can just use this, and we have defined it for Python and for Golang. So this is also something that we already have, but we could actually generate more helping functionality based on the JSON schema.
Okay, thank you very much.
Okay, so next one in the list is Manuel, please.
Yes. Hi, Jürgen.
Hi, Manuel.
Hi. Thanks so much for the nice talk. It was a very good overview. Yeah, so we are also working with Keptn, also in the project. Therefore, Benedek, yeah, had this specific question, and maybe Alessandro has even more specific questions for you. I would have one question concerning this event part. Is it in the end a publish subscriber system you are using? So to communicate between Keptn and the different tools?
Yes. We are using NUTS, which is a which is actually this message broker that we are using inside our Kubernetes clusters, but it's following the publish subscriber methodology. Exactly.
Okay, this is interesting because it can connect also to the question from Benedek, because if you analyze, for instance, what is happening in the publish subscriber component, then maybe you can also reason about these mappings now. Actually, which tools are now listening for what kind of events. And then maybe you can shift the static analysis to a more runtime analysis. Or maybe you have already such information.
I just want to show you where we are where we do have this information. It's not the information at runtime. It's more the information. I just pick one project here. It's actually the info. It's more the static information. Of course, since everything goes into goes through one channel, we could also do some runtime analysis and check how many deployment events, how many test events are actually going through Keptn. What we have come up with, one of the latest versions of Keptn, is here a more static view on which tool integrations do we currently have and for which events they are actually subscribed. So just as one example, the Helm service has a lot of different integration, a lot of different points of interest, maybe. So it's listening for each time where there is a service created, where there's deployment triggered, where's a rollback for releases. And some of those, they are listening for the triggering of the events. That kind of indicates when they are listening for the trigger, this indicates that they might want to be the active part. So they are listening for a trigger and then they act upon this trigger. For example, the JMeter service, whenever there is a test triggered, the JMeter service would act upon this. Others, maybe I have one, the approval service, but interesting here, the Litmus service, which is a chaos engineering framework, this integration is also interested when tests are finished, because when other tests are finished, like performance tests, when they are finished, this integration would also stop its own tests. It would stop the chaos. It would stop to mess up with my whole cluster. And so this is the way how we can connect the tools, and we can actually see this on a more static point, which tools are connected and for which integration or which types of cloud events they are interested.
Yes, very good. Thanks for the clarification. And thanks again for your great talk.
Yeah, you're welcome. Thanks.
Okay, now since I raised my hand, I give myself opportunity to ask you a question. In your slides, I think it was slide 19 and 20. I got an implicit assumption, no, here. So that basically in Keptn, anything you want to do assumes that you have a kind of running system. So whatever non-functional analysis, performance analysis, or reliability analysis, basically you need a system to be monitored. So you need to collect data, and then you have here tools, no, or whatever tools I see here. I don't know, like JMeter or any other tool. And then basically you are able to calculate, let's say, the indicators based on kind of running system, no? So I would like to know if you worked in any scenario where the connected tools and approach for the analysis of the system adopt any, let's say, not proactive, I have to say, kind of model-based approach. I mean, you can have here, I'm just thinking about performance, at least the domain I know better, no? So you can even try to assess performance before you deploy the systems, no? So imagine that the tool you are connected here in the ecosystem, no? For example, if you switch to the next slide. So so here I see that at that time you are auto-promoting your system, no? So here assume that you are not able to perform any design time, let's say, evaluation of the service delivery indicators, no? So for example, if you connect a tool that is able to, I don't know, perform performance analysis based on queue networks, you don't need a running system, no? You can even try to perform early analysis of the performance of the system, so before moving to the next stage, no? So the question is, did you work in any scenario where you connected any let's say pre-deployment analysis of the running system?
That's a very interesting part. So for Keptn, we never really considered this. I'm also thinking about you could analyze the software based on the I think it's the O notation, where you could basically check for runtime complexity, and this can be done without executing the software, or yeah, with a I think it could be done with a static check. But with Keptn, we did not really want to touch the whole part before it's really a container image. So we are not touching the part where it's doing unit tests or doing static code analysis. It would be a little bit, it would stretch even more into the whole software delivery lifecycle process. So we decided we want to start where there is a new container image. We then discovered it's not only working for container images, it's also working for monolithic applications. But just at the beginning, when we started with this open source project, we really tried to focus in the whole cloud native environment to fit there, because we saw the complexity there is a lot of different microservices, and orchestrating the delivery of a lot of different microservices is way more complex, and it's a whole other problem than orchestrating the delivery of one monolithic application. This is where we started to focus. But it could, of course, also be interesting in doing an analysis of some metrics before you actually want to deploy it, and then it would actually stop the deployment early on and not even start the deployment because it says you can do this. I'm not 100% sure. Maybe those tools are actually integrated in the IDE, and you could maybe base it on the same quality definition. So we could use the schema of a quality gate, like the SLO definition. We could use the schema of the SLO definition as the way how to define your software already as part of the IDE of a developer, so that we could integrate it there. But it's not, we have not considered this as part of Keptn.
Okay, so thanks for the answer. The next one, we still have a few minutes. I also we have the discussion session of 15 minutes until 12. So yeah, so we can just use part of it. So next one in the list is Alessandro. Please.
Yes, hello, Jürgen. Thank you very much, of course, for the presentation. Well, I'm interested, I reconnect to the question of Benedict Manuel, and I'm interested in the uniform. I saw that the last screen that you showed to Manuel, if you can go back there, this one. I saw that when I tried the last version of Keptn, there was not this this view with uniform. I was expecting, I knew that you were delivering uniform by Johannes Brouwer, but I was expecting that it was another JSON schema. So why it is not, you don't have done a JSON schema to describe what are the connectors that you're deploying inside, that are deployed inside the Keptn cluster? And why I couldn't figure out a JSON schema? It looked like that could be a JSON schema behind this view. And how could I query? Because I would like to query Keptn to have this, for example, as this view as a JSON. Is that possible?
I have to think about this. So to be honest, I do not know the ratio behind why it's not a JSON schema and why it's let's say this implementation. So yeah. It's I think it was just going for we had it in the beginning, we had it just as a mock-up, and we worked from the mock-up more into the implementation and not by defining a schema how the implementation would look like. It was more the UI based approach from a mock-up to the concrete implementation. It could be a JSON schema. I don't see any reason why it should not be able to do this. And yeah, querying the data from here, it's actually you would be possible to assemble all the data that's written here, and basically this one looks more like a list of different integrations. Would be very similar to this one because it's semantically it's also a list, since this is a wildcard here. So that should be absolutely possible to do this.
Yeah, but you now provide a right. Is it possible now? I mean, can I do a query via Keptn command line to query some event or something, and to have this as a JSON? It's not possible yet.
You can query the different kinds of events, but you can currently not query which tool integrations you have. So okay. in the Keptn CLI, you can get all the different events. So, but for the events, I just would need to switch to a different screen here. So just to
yeah.
So I will just take let's say one that was actually success. No, we can take the failing one anyway. So what you would be able to query is this list of events. So you would get the deployment events, you would get all these events, but you cannot, currently you cannot query all the tools that are connected to Keptn. So you would actually find it here in this event. You would see yeah. that that this is the Helm service that triggered this event. So it yes. would be more yes. of a fetching all the events, and then based on the list of events, you have to do some data massaging and to do some yeah calculation on your end to find out which tools are then really triggered on during runtime.
Okay, thank you very much.
Okay, so thanks Hugo for your presentation. We are now already in the last 15 minutes where the agenda we plan to have a discussion, I think, about all the presentation we had in the morning. I don't know if all the speakers are still here, and if you have any other, let's say, general topic to discuss that somehow is related to all the presentation we had in the morning. Otherwise, we can just go ahead a few more minutes, discuss about Keptn or as you like, and then we will stop at noon for the lunch break. I think I'm just checking who is here. I think it's only Jürgen's here, the previous speaker, or also Getza is here. I don't know if he can hear us. So if we have still some questions to Getza or Jürgen, we can go ahead with these questions, or I have another question for Jürgen, if you all agree, or raise your hand. And since I already spoken and asked questions, so I give precedence to your questions, if any. If not, I don't see any raise hand here. So my question is, Jürgen, did you perform? Did you collect any feedback from the Keptn community about the, let's say, usability of Keptn? So here we are in the low code, let's say, workshop, and one of the goals is to keep the, let's say, the tool simple for even user that we not necessarily have very specialized skills. Well, in this case, at least from my little experience on Keptn, and also with JSON, I mean, somehow you are expecting a lot of expertise from Keptn users, so they should be able to understand the technicalities of the underlying tool somehow, no? And yeah, and what did you, yeah.
Yeah, I think I can show some really good efforts that are currently, you should be able to see the screen again, that are currently going on in the Keptn team and also triggered by the community. And first, I want to show you like the, let's say, the traditional way and the way that most of the tool integrations have been built. And we provided a service template in Go that will give you the possibility to get started easily, but still you will see, let's say here in the event handlers, so you will just use this template and then fill in your business logic code. Like, let's say if you want to add your tests here, your test integration, this would actually be the function where you put in your business logic code, like how to trigger a JMeter test. But you still see there is a lot of different code, or it's a lot of other code that is here, and it's only the skeleton of the code and how everything is done. It's already 200 lines of code, and you might not be interested in everything, and it's very low level. So what we have come up with is another way to write tool integrations. And again, here we are using a lot of declarative approaches, and some automation is then done in the background. So instead of writing the whole logic of the tool and that there is a cloud event coming in and there is data to be parsed from the cloud event and then a cloud event has to be sent back, we now have a new way how to define integrations. And it's basically, I first want to focus on this part because it's basically just running a container image without the need to specify which data is coming in and which data is sent back. So you can just define, you want to run a binary. In this case, it's Locust. It's similar to JMeter. It's a load testing tool. So you could define, I want to run this, this binary with a couple of different arguments. And to define when this execution is triggered, you define this up here. So you define the matching of the event to when this integration is triggered. So in this case, when there is a test, when there is this kind of event, when the tests should be triggered, this integration would start its work. The good part here is you don't need to know how to write Go code. You don't need to know how to write Python code or whatever. It's really just this declarative part that you need to do. The image itself, a lot of different applications out there, they provide a Docker image with their tool already in it. Like there is an official Locust image, there's an official auxiliary image for also for load testing. There is an official, I think there is one image also for JMeter that has the JMeter binary already included, and you can just call it. And then the passing of the arguments from outside of the container to inside of the container to pass data from the cloud events to the actual execution, you can just do this with mapping environment variables. So we can create an environment variable with the name host here, and it will be populated with the value from the cloud event and exactly with the deployment URI, so that this tool integration knows where to send all the traffic to. And this is now a way that we want to promote more. It's a bit more limited in the functionality that it can do. If we have to think of a tool integration that has to do very complex business logic that cannot be done just with calling one argument or one binary, then this integration might not be the right way to do it. But a lot of different integrations, they can actually be written in the way that you just call one binary. The binary will be executed, and then based on the exit code of the binary, the integration around this will send back the correct cloud event, like a failed execution or a successful execution with details of the execution of the cloud event. So this is where we are doing, where we are creating ways to be able to write integrations without the need to know how cloud events are working, without the need to fully understand the JSON schema, to parse all the data, but doing this really in the most declarative way we could think of.
The very last short question. So basically, YAML, or in this YAML specification, it's like a DSL, no? What is your preferred? What is the tool you are using for editing? So it's.
I just use Visual Studio Code, and I do not have a sophisticated check there. I think it just checks for more or less for the syntax, but it does not check for the semantics. So I could, for example, here we cannot actually. It's defined by the Keptn team, so it's not an official resource that has a schema. If we think about Kubernetes resources, they mostly have a schema behind it, so you could do checks directly in the IDE or in the editor. This one does not have this, so there is still the possibility to make a typo here in the image, and you would not be able to check it at design time. You would only see it failing then at runtime. So this is a way to improve this.
Okay. Thanks a lot for your detailed answers, and from my side, no further questions. I already asked a lot, and yeah, we have just a couple of 2-3 minutes before the end of the session, so this is the last opportunity for all of you to ask a question to Jürgen or any other speaker if he's here, or otherwise we can close the session and then go to the lunch break. So up to you. Otherwise, I will apply the tacit consent policy. And yeah, okay, so we have no further questions here. And so I would like to thank again Jürgen for his nice talk and his detailed answers. And yeah, so we stop here now. And we will restart after lunch break, 1:30 p.m. So thanks for attending and talk to you soon. Bye.
Thanks, everyone. Bye.
Thank you. Bye.
Hello.
Hello.
Manuel, hi.
Hello.
Hello.
Hi.
So we are almost ready to restart. Okay, so here we go. Let's start with the afternoon session of the workshop. So this session is about the scientific talks, and the first talk is about Loli Burgueño. So stage is yours, please. Let me know if you can share the screen and everything works.
Thank you, Luca. You
Yes,
should be seeing. Yeah, thank you.
Works.
Thanks. Okay, so thank you everyone for being here to listen to my talk, and I will be about modeling a system. So the title is "No Need to Model Alone: A Modeling a System to Bridge the Gap Between Natural Language and Domain Models." Before we start talking about modeling, let me show an example of how powerful natural language processing is nowadays. This is an example that you all know, and it's the Gmail auto-completion feature. So let me show, for example, how it works for those that are not used to the web interface. So we start writing an email, and I start, for instance, with "Good afternoon, how are you, T?" And Gmail automatically auto-completes this or suggests an auto-completion which was doing well. So I accept it. I keep writing, and I say, I've been thinking about what we discussed last week, and I think that is very, and Google tries to suggest a good idea. Maybe this is not what I was thinking about, and I say this is a very promising topic instead of a good idea. I keep writing, and I say, what about meeting? And again, Gmail is suggesting next week, and maybe that's what I wanted to say. Then I say, looking forward to hearing from you. And again, as soon as I type here, Gmail autocompletes. It also autocompletes the best regards. And once as I have written my whole email, I go to the subject box, and it also suggests a potential subject that I want to add to my email. So this is just a clear example of something that was impossible a few years or decades ago, but right now all the power of natural language processing is showing that this is the future. So now going to talk about models, I'm going to present here our first attempt to autocomplete domain models. And let me first present what domain modeling is very, very quickly. So the idea of domain modeling is to turn informal descriptions of a domain into some structure and unambiguous representations that leaves out those superfluous details for the domain that it's being considered. And it usually is done using a concrete notation. So the motivation of this work is to promote and facilitate the creation and also the manipulation of domain models. So we are aware that there are a broad variety of languages and tools. For instance, we have DSLs, we have UML, we have entity relationships, diagrams. We have many tools. We have DIA, we have Magic Draw, we have the Eclipse modeling framework, and so on and on. But still, despite all these languages and tools, the models are still created by hand. So what I'm going to present in the next slide is this paper that I presented last week or 2 weeks ago at the CASE conference. So all the technical details, you can find them in this paper. So right now, many people say that data has better ideas. So the basic of this work is not that data does not always have better ideas, but they may have some ideas that can help us and assist us as modelers. So, and talking about data, once we are creating the domain model of a particular scenario, so we have data that comes from the requirements. We may have technical reports. We may have the slides from the client or stakeholder. We may even have the recordings from interviews and so on that we have had with them. And a part of this information about the domain that we are going to model, we also have some general knowledge information capturing sources such as Wikipedia, Google News, Reddit, and so on. So all this is just a bunch of textual data that one way or another we can exploit in the process of domain modeling. We consider in this work these two sources as independent. One we call the contextual knowledge, which is the text coming from the particular domain and their interest, and the other one is general knowledge. The goal of this general knowledge is to fill the gap that it's missing maybe in the contextual knowledge. For instance, machines are not like us human, and we can make assumptions that maybe those assumptions that we are able to understand as humans are not captured explicitly in the contextual knowledge, and maybe that general knowledge contains those. So for us, our scenario is the following. We have a modeler or an engineer that is creating his or her domain modeling and domain model. Our idea was, since we have this bunch of data, and we also know that there's a field which is called natural language processing, why don't we take advantage of it? So to put this a bit into context, natural language processing is a subfield of artificial intelligence, and some of its methods overlap with the machine learning, not all of them. So again, our idea, let's take all this data, let's provide it to a natural language processing algorithm or algorithms as we do in this work, and let's try to use this information and this knowledge to assist our domain modeler with the goal of make his or her task easier. So this is our approach. So our approach is we take all these domain documents that we were talking about, this contextual knowledge, we pre-process it. If we have audios, we have to obtain the transcript. If we have to also pre-process all the text, we remove, for instance, stop words like articles and so on that they do not have any meaning. And this is after this pre-processing step, we have a domain corpus of text. Now what we do with this text is to pass it to some NLP components. And in particular, we have two components. Let me explain the first one. First one is an NLP method for word embeddings. Maybe you're not very familiar with word embeddings, so I will try to quickly explain how this works. So word embeddings basically consist of taking some words, and from those words obtain a vector that represents them, and they are easily understandable for machines. The easiest embedding that we can obtain is to have all our bag of words and give one embedding to each word, like as easy as to the first word, I give a 1 in the first position of the vector and zeros in all the other positions. For instance, today could be 1 0 0 0 0 0 and so on. For the second word, we put the one in the second position, for the third in the third position, and for instance, for sailing, which is in the fifth position in this sentence, we put the one in the fifth position. So with this, we would have word embedding for the words that are in this piece of text. The problem with this method is one-hot encoding, but the thing is that these are very silly embeddings, so they do not contain any useful information, and there are more methods that are used and that help us with this. For instance, if we take all these texts, we can apply some word embedding algorithms, and we can create some encoding that encapsulates some information, for instance, about the neighbors of those words. For instance, in this case, if I take the word sailing and I train an algorithm with a window, for instance, 5, once I am training the word embedding for the word sailing, I'm also taking into account their neighbors. In this case, for instance, I've chosen a window with a size 5, and I can use, for instance, one of the most popular optimization problems to create the word embeddings, the gradient descent method. So after all this training process, for instance, this could be a possible word embedding for the word sailing. The advantage of using this more complex word embedding is that they capture some syntactic and semantic information about the relationship between words. For instance, relationships are linear in the vector space. And for instance, we can see here that there is some relation between woman and man, some relations between madame and sir, and so on. And those are aligned. And then now that we have this vector representation from these words, we can use the Euclidean distance as a measure of the relatedness between words. And not only that, but we can also apply some operations, and I can say, give me some word that is related to the word sir, and I might obtain the word madame, or give me a word which is related to men, and I can obtain men, woman, or king, or some words that usually appear together in the same context in the corpus of text that I have used to train these word embeddings. And I can also give, I've been talking about positive word, give me words that are similar to this one. I can also provide negative words. For instance, here I have an example, which is the vector of kings minus the vector of king plus the vector of woman, which is give me words that are related to kings and woman, but that are not related to king singular. And we might obtain a vector which is similar to the vector that represents the word queen. So as you can see, after this training, I'm keeping some semantic and syntactic relationships between words. And this is what we want to exploit here in our approach. So what we do is, once that I've explained this word embedding, we use this word embedding to create two types of models. These are not software models. These are not our domain model, but they are NLP models, which is a completely different thing. And we train one of these models with the contextual knowledge and another one with the general knowledge. And in this particular case, for the general knowledge, we have used the Wikipedia. So we are reusing the pre-trained model that Stanford University trained using GLOBE with the whole corpus of text of Wikipedia. And apart from this NLP component, we have another one where we use morphological and analysis and lemmatization. Very quickly here, for the morphological analysis, we use the part of speech tagging, and we need this only to know if one word is a verb, it's a noun, it's an adverb, and so on. And we also use the lemmatization process to obtain the lemma from inflected forms. This is very linguistic terms. But for instance, imagine that I have the word flyers and I want to lemmatize it as a verb. The lemma could be the verb fly. But for the same word flyers, if I lemmatize it as a noun, I would obtain the lemma flyer. And we will also need this in the future as part of our approach. To do this morphological analysis and lemmatization, we have used WordNet, which is a lexical database, and it's also part of the Python NLTK. So we are using the API to query and to do this step. So now that I have explained the motivation, what are our sources of knowledge, and the NLP component that we use, let's focus on the core of our proposal, which is our model recommendation engine. And let me explain this with an example. If you remember the Gmail example that I gave you, let me go back to it and say that you can see that Gmail does not provide the whole email for us, because that could be maybe unrealistic and so on. So here we are following the same approach. We know that in literature there were some approach in which the requirements were fed to some algorithm and process, and the whole domain model wanted to be provided, but maybe that model is not what the user wants. So we are moved toward a different approach in which we assist by means of recommendations, like the same way that the Gmail and many other technologies do for us. So let's assume that we are building a domain model, and we have here this partial model, which has two classes, a pilot and a flight, and one relationship between them. So the first step of our model recommendation engine is to slice this model. So we built several slides. I will explain them later. For instance, for this particular class, we obtain one slice per each class in the partial model. So we have one slice that contains only the class flight, one slice that contains only the class pilot, another slice that contains the class pilot, its attributes and its dangling references. In this case, there is no attribute, but if there were an attribute, it would be there also. We do the same for the class flight, and we also build some slices for each pair of classes. As I will explain later, each slice has its purpose. So once I have sliced the model, just seeking to provide useful recommendation for that particular piece of model, what we do is we query our NLP models with the goal to obtain potential concepts related to those concepts. So what we do is we have sliced these models. For each slice, we extract the concepts. For instance, the class of the name, the class on the name of the class, the name of the attributes, the name of the relationships, and we use these words to query the NLP models. And the NLP models will give us just some related terms. For instance, here we're talking about flights, pilots, and so on. If I query the NLP models with the word flight, the NLP models give me the words flights, plane, pilots, pilot, flying, flight, airline. So we see that they are words that are specific to the domain we are dealing with. So next, what we do is we refine these words. For instance, if we have created this slice with the goal of recommending new classes to add to the domain model, we are not interested probably in words that are plural forms or in adverbs. So what we do is we use this morphological analysis and lemmatization, and we will refine this list of words. And for instance, for flight, after the refinement, we keep the words plane, airline, airplane, jet, flying, and fly. The next step could be to build new potential model elements, because right now we only have concept words, but we need to see if these are classes, these are attributes, where do I have to add them, and so on. So what we have done right now is, as I said, we have different slices with different purposes. So we have sliced this model according to several patterns. I'm going to focus on the first one, and for instance, say that the one slice that we create contains all the classes in the model after removing their features, which are attributes and relationships. And this type of slice is aims to suggest new classes. Therefore, as I said also before, we remove verbs, we remove adjectives, we remove plural nouns, and so on, and the remaining words are the potential candidates to become new classes. Without going into many details, let me also say that we have one slide for each class C in the model. This type of slice, where we keep attributes untangling relationship, aims to suggest new attributes for that specific class, and we have one slice for each pair of classes, whose aim is to suggest new relationships and so on. As again, more details in the paper. And imagine that for the particular case that we were talking about, our model recommendation engine suggests to add a new class named plane, or to add a new class named airline, or a class named airplane, and so on, so on. So once we have all these suggestions, we provide them to the user, and the user picks one. Let's assume that he picked to add a new class named plane. The partial model is updated. And this is not all, because we also store the feedback. So every time the user accepts, rejects, or even ignores a suggestion, we keep track of that. If you remember when I explained word embeddings, we can keep track of negative words, and we can provide them to when querying our NLP models, and say, hey, give me concepts, give me terms that are related to this one, but that are not related to this one, because we already know that this one was rejected by the user. So we already know that he's not interested in going into this direction. So that's why we keep this historical data and the feedback from the user, and we use this feedback when building our suggestions. And now let me show the preliminary validation that we have done about our approach. This is an industrial project from 2015, which is a water supply company from the Malaga town hall, and they wanted to introduce a notice management system to control incidents. The documentation that we had at that moment in time was a presentation from the client, 21 slides, some paper forms that they wanted to have replaced with an online form, and the software requirement specification, which was a document with this number of words. And since this is an old project, we already have the domain model that the developers manually produced. So we have used this case to study the functioning of our approach, and we are particularly interested in studying the recall, the precision, the source of the accepted suggestion, whether they come from the context or general knowledge, and the performance of our approach. So we haven't performed an empirical study with users, but what we did in this preliminary validation was to try to automate the reconstruction process. So what we did was we tried to simulate the behavior of a designer, but in the very strict sense. So since we have the final model, we started from 5 models, each one of them containing one single class with no attribute extracted from this model. So we have run 5 different experiments, and starting from these models, each one with one class, we automatically accepted or rejected the suggestion depending on whether they appear or not in the final model. Of course, this is not a very realistic scenario, because in reality we expect the user to interact and to also contribute to building the model. So this is why we regard this evaluation that we perform as the worst case scenario, as in the end it's only the machine accepting and rejecting suggestion. Okay, so for the recall, after this experiment, we realized that 62% of the model was reconstructed. On average, it was 34 out of the 50 elements that it contains. So this was the model that that we were able to reconstruct. As for the precision is kind of low. It's just a bit over the 4%, but we also think that this has an explanation. So the NLP models were queried 15 or over 15 times. You can see some decimal numbers here because we computed the average of the 5 experiments. So these are average figures. So for each one, it was queried about 15 times, and we asked our model recommendation engine to provide 20 suggestions per source of knowledge. It means that in total, we received an average of over 100 suggestions, out of which only 25 more or less were accepted. But if instead of looking at the overall number of suggestions received and accepted and so on, we look at the number of suggestions that were accepted per every query is more than 179, which means that this bot that we built was able to accept 1 or 2 suggestions more or less from each batch of suggestions. With respect to the source of knowledge, we observed that around the 85% of these suggestions were coming from the contextual source of knowledge, which makes a lot of sense, but 14% were coming from the general source of knowledge. One example could be the user. For instance, in the final domain model that we obtained that we got from the client, there was a class called user, but nowhere in the documentation the name user was mentioned. So that was something that the developer came up with. So that's a clear example of why the general knowledge is needed. And for the performance, we can say that all the components in the model recommendation engine take under 1 second, which is very efficient. The training, loading, and querying the NLP contextual model just takes a few milliseconds. What's more expensive in this sense is loading the NLP general model, which takes 32 seconds. The good thing about this is that it is only loaded once at the beginning. And then querying this model, which is very big, it contains all the embedding of all the words in Wikipedia, takes a few seconds. We have used right now the implementation from the Python implementation, but we also plan to have a look at the C implementation that we believe will be more efficient. And to conclude this piece of work, this is a first step towards a model recommendation engine that we feed with the textual description, and it's promising. It seems to be promising to generate auto-completion for models under development. And our idea would be to be able to build a modeling assistant that helps us build models faster and also of higher quality. And for the future, in this work, we plan to integrate other type of information, for instance, past models, ontologies such as Sumo, and so on. We would have to work on the usability aspect. As I said, we have created right now a model recommendation engine, but we haven't started thinking about how to present this to our users. And we also plan to perform a empirical study. We would like to refine the techniques that we have presented in this paper, the slices that we create, the NLP components, and so on. And we would also like to apply this to other languages, modeling languages, and so on. And just to finish, let me also say this wasn't the goal of my talk, but with all these amazing co-authors, we published also a work which is the result of 1 week of working together, in which we try to create this conceptual framework to identify the foundations for intelligent modeling assistant. And here we try to capture what what are the main components and properties that an intelligent modeling assistant should take into consideration. For instance, external sources like data, information, and knowledge, also the experts, the socio-technical modeling systems, the intelligent modeling assistant, which is the core, the engine that I've been talking about, how the communication between all these components is done, and also the properties that they must fulfill in terms of quality, degree of autonomy, and for instance, the relevance, the confidence, and explainability of the suggestions, and so on. And also, you can find more details in this paper below. And thank you very much for your attention.
Thanks a lot, Lolly, for your great presentation. So we have plenty of time for questions, almost 15 minutes, I will say, and I just already see some raised hands. First one is Manuel, please.
So, Lolly, thanks a lot for this presentation. I really enjoyed it. Yeah, it is very impressive. I may have many questions, but let us start with a few, and then maybe we can catch up also on a different channel. So I have one question concerning if you have this feedback of the modelers also incorporated, how they deal with recommendations. I'm wondering now, because we also now talking a lot about low-code development platforms, so you may have a platform that is used by many modelers, or maybe you have a dedicated instance for one modeler. So if you now consider this feedback from the modelers, do you foresee to have a modeler-specific recommendation engine, or for a particular project, or for the whole platform, or can there be different levels here?
There could be different levels, indeed. Yes. We haven't started thinking about how to do this, but we have discussed these possibilities, because in the end, we have one developer working with one instance, but we may have a group of modelers working on the same project. As I said, one of our future lines of work would be to take into account past projects. Past projects means more information, more knowledge to integrate into this. So yeah, and this could also be configurable. For instance, you want to receive suggestion for your own models, you want to receive suggestion from knowledge that we have extracted from all your company, from all open source projects available there. So yeah, that's a very interesting question. We don't have specific plans, but for sure that should be taken into account.
Yeah, because it's a topic also in this project, how to deal with such a platform. If you have many users, what can be shared, should be shared. Then another comment I have is the usage of or reuse of ontologies or other kind of artifacts. Maybe we can see if it makes sense to reuse Extremo here. I'm not sure if you are aware of this tool. It was a collaboration together also with Juan de Lara and a PhD student of his group. And here was the idea to have a model reuse assistant that can make use of ontologies, for instance, but also XML files, because especially in these automation domains, you have very large component catalogs that can act as a kind of library for modeling purposes. So we have here an integration framework that integrate the different sources, have a unified representation that can be used in EMF. So I assume you have developed your approach for EMF, or yeah. Yes. Okay, so maybe you could already plug Extremo into your tool, and then you can have support for OWL ontologies, XML schemas, and I think we even have a few other formats that you can use. for recommendations.
Yeah, that is very interesting. In fact, Manuel, before we started thinking about using NLP models such as Globe, word embeddings and so on, the first thing that came to our mind was to use ontologies. And we faced the problem that we didn't find very rich ontologies covering many domains and so on. We saw that there were ontologies focusing on particular topics, but not like general knowledge, or maybe I'm working with this specific domain and I might not have an ontology that covers the topics of this domain. So that's why then we start exploring other possibilities and word embeddings and so on. But we somehow deep down we still want to use these ontologies. I talked about Sumo because I thought it was one of the most complete ontologies nowadays, but I wasn't aware of Extremo. So for sure I will have a look at it, and if it provides some easy integration with BMF, that would be great. Yes, thank you.
Yes, I think it really depends what kind of ontology you would like to reuse. Now you have these upper ontologies that are very abstract. That can be a good orientation for modeling, but if you're in a particular domain, what we used, for instance, is the E-class standard. That is a very huge standard about classification of automation components you have. So it's an industry standard for a very particular domain that is used, for instance, for ordering automation systems, where you need a kind of ontology to specify what components do you need. I think combining all of these different techniques is very interesting. And also your results, you have shown that the how do you say, the domain-specific artifacts, they can contribute a lot, but also the general knowledge can give you additional recommendations that are useful. So I found this result very interesting and promising to combine this different kind of information we could reuse. I have seen now Juan already posted in the chat the link to the Extremo.
Thanks.
Work. Yeah. Thanks, Lolly, for the nice presentation. Now I give the floor to the others to ask questions.
Thanks, Manuel. The next one is Illyrian, please.
Thank you, Lolly, for the inspired motivation. I will just also add to Manuel. There is also, I think, Samos tool that is also based on natural language processing. It converts models to documents, then it uses NLP, so information retrieval, and so they measure the frequencies of the words within the sentences, but it takes also in consideration the structure of a model to produce recommendation. Actually, it doesn't produce recommendation, but it is used to find model clones within a repository to get what is similar within existing repository. But also related to this, I have a few questions. So first, do the user has always to provide this domain-specific documents in order to get domain-specific recommendations? Do the user has always to fill the engine, your algorithm, with documents, relevant documents, in order to get this domain recommendations?
Yes, right now you have to provide domain documents. Otherwise, you will only receive general knowledge document recommendations. Recommendation from the general knowledge.
Because I thought that, well, that could be a problem for classes like user or person, which are very similar to different domains, and then you can get recommendations which are not perfectly matched within a specific domain. And that I would have also one concern I didn't understood, maybe when you provide recommendations in the integration part in the end. Let's say you had this fly class, and let's say airplane. Can it be as an attribute, as a related class? Because let's say if you have a class pilot and a class, let's say stewardess, and those classes may be connected with a class, let's say staff, And can then this stuff be integrated as an attribute directly, which actually should be, let's say, a superclass of this pilot and stewardess, and it could be a constraint problem then. So
yeah,
so I mean, is this constraining problem in the integration part handled here in this algorithm? I didn't got it maybe.
Yes, we also recommend attributes and relationships. If you remember this slide, I can go back. This slide, I presented some of the slices that we create from a partial model, and each slice has some purpose. So there are some slices, like the first one, which aims to suggest new classes, but for instance, the second one that I'm presenting here aims to suggest new attributes. So once we have recommendation from this type of slices, what we will provide to the user will be, hey, do you want to add a new attribute with this name to this particular class?
Okay, thank you, understood. Yeah, thank you.
You're welcome.
Okay, great. So the next question from Francisco, please.
Yes, hi Loli, Francisco here. Thank you so much for the presentation. It was so nice. You have actually commented that your natural language model is backed by the WordNet lexical database, right? Right now, if I also recall correctly, you use it for stemming and cleaning word purposes, basically at the beginning, right? A pre-processing step. But I am aware that WordNet also maintains a tree of related words, right? By means of hyponyms and hyperonyms. That is, well, thereby creating kind of a hierarchy of words, right? So you may envision that under color, for instance, you may find red or blue or other more concrete instances. You get what I mean? Yes. Have you considered perhaps using this in order to improve your suggestions? For instance, I can imagine at least that you could use it potentially for supporting inheritance, for instance.
Exactly. Yes. Well, the first part, we do not only use this. I mean, we do not use this for the purposing, but for the refining. So we use WordNet to refine the set of words after we query the word embedding models. But yes, as you say, this WordNet has this kind of information, and you have also noticed that we haven't taken into account here inheritance, but of course that could be a great idea to use WordNet in this sense, as well as ontologies. So yes.
Okay, thank you. That sounds promising.
Thanks.
Okay, then I saw for a while hands raised by Juan. I don't know if he wants to.
Yeah, actually, my question was very much related to what Paco has just questioned. Well, first of all, Loli, thanks a lot. I enjoyed a lot also the presentation. So my question was exactly that. So I saw that in your use case, you had a couple of inheritance relationships, and I was not sure whether you were able to reconstruct those, because I noticed that you didn't, in your list of slices, you were not targeting specifically inheritance relationships, but I also noticed that you were using WordNet, and I was wondering whether using these hyperonyms and so on could help for that task.
Yes. As I said, we haven't focused here on inheritance or composition or aggregation or even data types. So we are not considering those right now for our domain models. It could be the user who had to complete this information. But of course, we will have to find ways to come up with how to create this information and how to provide richer suggestion. And indeed, WordNet would be a great idea, complemented with some ontologies to achieve this.
Yeah. Now that we are talking, I also have a curiosity about, did you integrate this with any tool, maybe Papyrus or something like that?
Good question. No, right now we are using just Java, and we are not we haven't worked on the on the user interface. Actually, in fact, we have hired a person now that is working on improving this prototype and making it usable with a nice interface. So right now we are using just EMF with the EMF API in Java, and we query these Python models. So we have both of them, but we plan to create a Flask server to put all the Python code there, or C code there, depending on what's more efficient. And then to create a nice, I mean, we have the engine, we plan to create a nice interface. Probably we will keep using EMF, but we don't know which technology we will integrate it right now. So that's totally future work. We have to think about that.
Thank you.
You're welcome.
Okay, great. So I think we are perfectly on time. Thanks, Lolly, again for your talk.
Thanks for the invitation.
Great. So now we can move on with the last talk of today by Jesus. I think he's here. I don't know. Jesus? Ah, yes, I see you. But you are muted.
Okay, I'm here. I'm trying to put the camera.
Okay.
What is it working? No.
Not yet.
Damn it. Okay, so well, anyway, I'm going to share the screen. So
yes.
I think no, I can go without the camera. So I'm just going to share the screen. Can you see the screen?
Yes, it works.
Okay.
Great.
So in this presentation, I'm going to talk about transformation engine that we have built for the ADL model transformation language. And this transformation engine has two main features. One is that it automatically parallelizes model transformations, and the other is that it automatically applies optimizations to improve the execution time of the transformation. So the context of this work is model-driven engineering. And as you know, in model-driven engineering, models are the primary artifacts that we use. And what we do is to use model transformations to automate the manipulation of these models. Typically, we use model transformation languages, for instance, Epsilon or ADL, and these are dedicated languages which provide specific features, specific constructs to help us build these transformations. In particular, in this work, we use ADL, which is a widely used transformation language. And our focus is to improve the efficiency of the execution of the transformations. However, it is important to note that if you are going to transform a large model with millions of elements, the problem of executing this, of executing a transformation against this input model efficiently is something that you have to deal with even if you use a general purpose language like Java. The question is that if we use a higher level language like ADL, this provides us opportunities to perform automatic optimizations. And this is the focus of this work. As a concrete example, and to give a very brief introduction to ADL, let's consider this model transformation, in which what we do is to transform between the abstract syntax of Java. For instance, we have a piece of Java code like this one, and we represent this code as an abstract syntax tree. And then we apply a transformation to reverse engineering this Java code into a UML model, right? So probably in ADL, we are going to have to write rules like this one. So here we have a rule to map Java packages into UML packages. So basically the transformation matches all Java packages, and for each Java package, it creates the corresponding UML package. Also, we have rules to transform between Java classes and the corresponding UML classes. And then in the body of the rules, what we do is to write OCL code intended to gather input elements which are used to initialize the features of the target elements. For instance, here we take the name of the package and we assign the name of the Java package to the name of the UML package so that both names are the same. But here in this assignment, which is called a binding, what we do is that we take all the elements of the package, we filter the elements, and we get all the Java classes. We use an OCL expression to perform this filtering. And when we have all these classes, we tell ATL, hey, we have Java classes to the right of the binding, and please give me all the UML classes that correspond to these Java classes. So the ATL engine is in charge of getting all the target UML classes and assign them to the classes reference. So basically, this is what the way in which we write model transformations in ATL. So in this presentation, what I'm going to talk about is about how to improve the efficiency of the execution of this type of transformations. And this is based on a work called efficient execution of ATL model transformations using static analysis and parallelism, which was published in IEEE Transactions of Software Engineering, and it is a joint work with Loli, who has just presented, Manuel, and Antonio Vallecillo. And in this work, what we did was to create a compiler for ATL, and then this compiler basically implements or generates codes for a parallel execution algorithm, which is a different execution algorithm than the original ATL algorithm. Also, the compiler applies automatic optimizations to the OCL code. And what we get in the end is that we were able to obtain large performance improvements, as I will show. So this is the architecture of the compiler. Basically, it is a very simple architecture. We have an ATL program. We perform static analysis to obtain like type analysis and rule analysis. I will explain a bit more about this in order to obtain additional information about the transformation. And this is used by the compiler in order to perform optimizations. Okay, well, the static analysis information is put in an extended ATL model. This is used by the optimization phase to rewrite the code in order to make it faster. And then we compile the ATL code into Java. And we generate a number of artifacts like a runner to configure the transformation so that the user can configure the transformation and specify the input and output models, a preprocessor, which is in charge of taking the input model and putting it in a proper form for the transformation to be executed. This is the transformation code, which is executed in parallel. And then it is a post-processor, which is in charge of taking the output model and perform some additional task in order to resolve references or to put the proper root element and so on. I will talk about this a bit more. So it is important to take into account that to create this parallel compiler and to create these optimizations, there are some features in ATL that make it possible. One of the features is that rules are matched at the top level. This means that all the rules in ATL basically could be executed at the same time. And this is because only one rule can match an input pattern. This means that the input patterns and the filters of the transformations of the rules has to be disjoint. This means, for instance, in this example, that we cannot have two rules for packages because we can only match one package, one specific package object at a time. The other thing is that the transformation is read-only and write-only. This means that we can only read the input model and write the output model. We cannot read the output model, for instance. Also, another feature is that it uses OCL for model navigation, and this allows us to perform very specific analysis to create the optimizations. And in particular, we use an analyzer to perform the static analysis, and this provides us with additional information to perform the optimizations. So regarding the static analysis, let's consider this piece of ATL transformation. This is a bit more difficult than the previous one, but basically we have a rule for mapping Java packages into UML packages. We have a filter here, and we have some bindings. So what an analyzer is able to tell us is that, for instance, this expression, p dot own packages and all these select filters, an analyzer tell us that what we have when we evaluate the expression, what we have are Java packages. And this is important because this allows us to reason specifically about this binding so that we know that this specific binding is only going to be resolved by this rule, package to package. And the same happens with this. We know that, or an analyzer knows that this is a call to an operation on proxy classes, and this returns classes. So this is going to be resolved by this rule. So we can use this information to perform optimizations. Okay, so now I'm going to explain the parallel execution algorithm. So before that, I would like to very briefly explain the original ATL algorithm. Basically, the ATL algorithm has two phases. In the first phase, it matches input elements and create target elements. So if we have this rule, Java classes to UML classes, the ATL algorithm does this. Basically, it traverses all the rules in the transformation, gets elements that match the input pattern, and create the target element and create a trace link linking this element here with this element here. Then in a second phase, what it does is to traverse all the trace links, and it recovers the transformation rule that has created this trace link, and now it executes all the bindings in the rule. And now the important thing is that, for instance, in this binding, when ATL evaluates this OCL expression, it has a set of input elements, and then ATL goes to the trace links to recover the target elements that has been created and assign that to the target element, to the target feature, right? So basically, the important thing is that it has two phases, and basically it's based on trying to pull element from the model and try to create trace links for them. So what we need is to find parallelism in this algorithm, and the main sources of parallelisms are that the rules are matched independently. This means that we can try to parallelize this loop, and also that we can resolve references, or that we need to resolve the references only after all target elements are available. So what we do is to split this algorithm, instead of two phases, in three phases: a pre-processing step to set up the model, an execution step to match elements, and in this case, in the execution step, we do execute the OCL code, and then a post-processing phase in which we only resolve references. So this is the algorithm that we have implemented. So we have all the we do the pre-processing of the model. So we put all the input elements in a buffer. Then we traverse all the elements in the buffer. And then for each element in the buffer, we call the execute function. The execute function basically check if there is a rule that can transform this element, and then it executes the rule. An important difference with respect to the original ADL algorithm is that here the rules here what we do is to give the elements one by one to the rule instead of asking the rule to go for the elements. And what this allows us is to parallelize this for loop using a data parallel approach. And then the execution of the rule means to create the output elements, evaluate the OCL expressions, and instead of assigning the result of the OCL expressions to the target features, we add this we add the result to a list of pending tasks that we execute when the transformation has finished. So I'm going to try to illustrate this with an example. Let's imagine that we have an input model like this one with 2 Java classes, a Java package and a Java field. In the previous example, we don't use Java fields, so in the pre-processing phase, we eliminate the Java fields to make the buffer smaller. Now, we set up 2 worker threads so that each thread, in this example, is going to receive elements to transform. So for instance, the first thread receives a Java class, so it executes the corresponding rule, creates the target element and the trace link. Then, at the same time, probably, the second worker thread receives another element, in this case, a Java package, execute the corresponding rule, creates the trace link. In this case, it needs to resolve this binding. So what it does is to add the corresponding classes to a set of pending traces that needs to be resolved after that. An important thing is that how we coordinate the worker threads. Basically, we have an atomic counter, which is in charge of counting the element the next element that needs to be given to a worker thread. So at the beginning, this counter points to the first element, which is given to this thread. Then we increment the counter and we give that to the other thread. So in this way, we are giving elements to the threads, giving work to the threads. At the end, what we have is a partial output model, in this case with a UML class and a UML package. And what we need to do is to complete the model, resolving the references by looking up in the trace model. Okay, so basically this is what we do in the parallel execution. The architecture for doing that is this one. So what we have is an input model. We put the elements in a buffer. We have the atomic counter that coordinates the access to the buffer for the different threads. And for each thread, we have a different instance of the transformation. And each instance of the transformation has its own local cache, a set of pending tasks that need to be done at the end, like for instance resolving bindings, and a local trace. And in the post-processing phase, we use all these, we merge all the local information to configure the final output model. So this is basically the idea of the parallel algorithm. Now the second part of the work is a set of optimizations to improve the execution of the transformation and the OCL expressions. So we have 3 types of optimizations. Optimizations at the transformation level, which are related to how we use and how we execute the rules. Optimizations at the level of OCL. And here main thing is that in OCL, there is an intensive use of collections. So what we do is to use an immutable library of collections, in this case, Java Slang. However, this is not enough, because many times what we are doing with OCL is to create many intermediate collections, and this put a lot of pressure in the garbage collector. So what we did was to optimize the use of collections, trying to use mutable collections like a regular Java array list instead of these immutable collections. For instance, consider when you have to use an immutable when you are using an immutable library of collections, the more efficient way to add an element to a list is to put it at the beginning. But many times in OCL, what you do is to add the element at the end. So this is also something that we try to solve with the optimizations. And the third optimization is automatic caching. So now I'm going to give you some examples of this. In the case of transformation level optimizations, one of the things that we do is to execute to try to match the rules in a specific order using an heuristic. And the idea is the following. Instead of using the order of the program to try to match the rules, what we do is to try to match those rules with a simple filter. And the idea is that if we fail when we match a simple filter, we don't lose much because it takes very little time. However, if we succeed and we actually match the rule, then we have the result very soon. The other strategy is what we call transformation footprinting. And here's the idea is that what I have already said, we give the transformation matcher only the elements that are mentioned in the rules. Also, we do some precomputation of expressions like all instances instead of going all the times to the model to get the all instances of a given type. Finally, another optimization is trace footprint reduction. And here the idea is that in the algorithm that I have shown, all rules create trace links always. However, what we do is to compute trace links only when they are needed by some rule. And this is also important to reduce the memory footprint of the transformation. Regarding OCL optimizations, here the idea is to identify common model navigation patterns and try to, as I said, try to replace the use of immutable collections by the use of mutable collections. To do this, first we need to perform escape analysis. I'm not going to be into the details of this, but basically this means that we need to know whether a collection is shared, a pointer to a collection is shared or not. In OCL, this is typically not the case. Normally, what we do is to write expressions like this one. So as you can see here, what we do is we take a list of elements, perform a select, and then we get a resulting collection. We apply a collect to get another collection and another collect to get another collection. So as you can see here, these intermediate collections are never shared. So instead of creating two intermediate collections, what we can do is to write this piece of imperative code. We do a loop over the original list of elements, and instead of creating many intermediate collections, we apply the body of the operations like not proxy and the collect directly to the in the body of the loop. In this way, we save two collections, and we just put the result directly here. So now I'm going to very briefly show you some of the optimizations. For instance, here we call this mutable addition. And here what we can do is when we have a select and then we include an element to the previous collection, we can do that directly to the final collection instead of creating a new collection, intermediate collection here. Filter and check existence. This is also a very common pattern. We perform a filter over elements, and then we check if there is an element of with a certain property. So here we don't need to create any collection. We just traverse the list of elements and perform the checks. And if we find the interesting element, we just break the loop. This is a similar optimization when we have a set of filters and we just want to count the number of elements that satisfy these selects. So we can do this with a simple loop. Filter and map. This is also very common. We have a select and then we apply several collects. So this is what I have already shown. This is a more difficult optimization, and here the idea is that sometimes we have some access patterns in the transformation, like this one, that we can pre-compute in the pre-processing phase. So what we do is instead of executing this each time in the transformation, we pre-compute an index in which we use the name property as a key, and then we just in the transformation we just need to query this global context, which basically contains the index. So these are the OCL optimizations. Another optimization that we do is automatic caching, and here the idea is that many times we have the same sub-expression in a transformation that need to be evaluated in several places because there are several paths in the transformation, for instance, that reach the same expression. So what we can do is to use attribute helpers in ATL to cache the results, but you have to do this manually. So what we do in the compiler is to identify these hottest spots, that is those parts of the transformation that are likely to be executed several times and are going to give the same results each time. And then we perform caching automatically. So for instance, here, imagine that we are doing this operation, this for all to the own class reference. This body here, all this part here is exactly the same regardless of the value of C1. So what we can do is to compute this value, put that in a cache, and then each time instead of evaluating this each time, we just get the result of the cache. And this is a very good optimization because sometimes it can reduce the execution time a lot. So regarding the evaluation, what we did was to compare the standard ATL engine, more modern and faster ATL engine called EMF-TBM, which is based on a Git, and our implementation. We use these 7 case studies, which are of different nature. For instance, here we have a reverse engineering transformation. Here we have a mapping transformation. This is also a very simple mapping. Here is an imperative transformation. This is based on doing a lot of OCL queries. So there are a variety of case studies. And the results that we get regarding the impact of optimizations, not the parallel execution, is the following. If we compare our implementation without optimizations against the faster ATL engine, which is EMF-TBM, what we get is a very important speed up. But if we also apply the optimization, we see that the speed up is even better. So for instance, in the fine couples transformation, it is very impressive the optimization that we get, and this is because the automatic caching. Also, for instance, here we get a very good speed up. So this takes for EMF TVM to around 1 minute, almost 1 minute, and in our implementation, it is less than 3 seconds. So what we can say is that the optimizations, the OCL optimizations that we perform are very useful to reduce the execution time. Regarding the impact of the parallel execution, what we have done is to execute the case studies using up to 12 threads in a machine with 6 cores. What we get is, in general, a very good scalability, because as you see, this is almost linear. But in some cases, the speed up that we get is not as good as we wanted, and this is basically because these transformations has a requires more work in the post-processing phase, and this cannot be parallelized as well as the normal execution phase. But anyway, I think that in general the parallel execution pays off. So just to finish, some lessons learned. So regarding the compilation of the ADL transformations, what we need to make this work is type information. This was a bit challenging because ADL was designed as a dynamic language, and by using an analyzer, we were able to cover most of the cases, but it would have been much easier to use a language like QBD because it is already statically typed, so it is easier to support the implementation. It is easier to support the implementation of optimizations when the language is already statically typed. So what I would say is that for future model transformation language, let's make them static languages, because this allows us to make more useful things, from analysis to optimizations and so on. Also, we try to be as compatible as possible with ADL. So as I have said, we support a lot of ADL features, most of them. But again, this is something difficult to be 100% compatible. And finally, regarding the automatic parallelization, that was possible because ADL is actually a DSL. So if you think about, ADL is actually a DSL specifically designed for creating transformations, and the types of rules that ADL has allows us to perform automatic parallelizations. If ADL were an imperative language, then that wouldn't have been possible. Regarding the execution part of the work, the post-processing phase is the main bottleneck. We were able to parallelize part of the post-processing phase, but that's not enough. So we need to improve how we resolve references in the post-processing phase. Also, what we show is that our implementation, our approach is competitive against using general purpose languages. And this is because you may think that you are going to do it better if you just use Java, and in some cases it can be easier to implement your transformations using Java, for instance. But when you have to optimize, it is you have to do it manually, and this is hard. And if you want to make the transformation parallel, this is even harder, and it is very error prone. So what our approach allows is to allow us to write our transformations without thinking about optimizations, without thinking about parallelism, and we get all of that for free. And finally, regarding how to analyze the performance of your transformations, so the first thing is that you have to think on the impact of your code when you are compiling the transformation. So typically, the best strategy is to write a very simple example, a algorithm version of your of your target code, for instance, in Java, and then use the debugging tools like Visual VN or Perf to perform the debugging. And a very important lesson that I personally learned is don't trust anyone, because we found out that in EMF, iterating backwards is faster than iterating forwards. So when you are debugging your transformations for performance, sometimes you may get very surprising results. So don't think that you are wrong. Maybe the APIs that you are using are wrong. So just to conclude, so I have presented our optimizing compiler for ADL. So what we do is to take advantage of the high-level features of ADL to perform specific optimizations. And as future work, we would like to find more optimization patterns and perhaps apply these ideas to other languages. So that's all. Thanks. So please, any questions?
Thanks a lot, Jesus, for your presentation. So yes, we have time for discussion, for questions. So Juan, you are the first raising your hand.
Hello, Jesus. Very impressive work, I should say. Congratulations, it was really nice work. So I have just a couple of questions. So I am curious about the slide 28. With the table with results.
Yes, the one?
Yes, that one. So why is it that in identify you have the optimization works worse than not optimizing?
Oh, okay. I don't remember exactly, but the question is that this transformation does very little, and sometimes the optimizations try to optimize for the let's say for the complicated case. That imagine that to perform imagine, I'm not sure if this is exactly the case, but imagine that what we do is to perform a catching of some expression, right? Applying this optimization has a small cost, but if this cost is never recovered, because the transformation is so simple that it does basically nothing, it only matches things and assigns things, then the small time that you lose in the execution trying to apply the optimization is lost.
I see, yeah. Makes a lot of sense, right? And also another question that I have with this experiment. So is the second column is the size of the model.
Yes.
And so the speed ups, did you see a kind of relationship between needs transformation between the size of the model and the speed up? So is it, I guess it's much better to use your approach with bigger models, or?
Yes, well, there are two things. Yes, it is better. Of course, if you to realize the improvement, you need either large models like this one for find couples, identify, and so on. But for instance, air quality, it's a small model, but the OCL expressions are very convoluted. So basically, it is like not a complex algorithm, but it has a lot of select, collect, and so on. So if you have large models, then it's going to pay off. If you have small models but complicated algorithms implemented in OCL, it may also pay off.
I see. Yeah, because the speed up is not, for example, from identify to Java to graph. So you have a bigger model, but the speed up is
yeah, because there is a balance between the size of the model and what you do with the model. Because many times the problem is that, for instance, if you take Java to graph, it is a large model as in Java to UML, but what we do here is less than the OCL expressions that we use here are less complicated the OCL expressions that we use here in Java 2 UML. So it depends a lot of what you do with your OCL expressions.
Right, yeah, I see. And another question, which is a little bit more about the possibilities of your technique. So you have shown this for APL. You have at the beginning mentioned a couple of things that you expect from the language. But could you apply this to in-place transformation languages, rule-based like Hensing, and what of these optimizations and parallelization would be possible there?
Yeah, well, I guess that you can imagine, I don't know, a language, an in-place language with OCL. All the OCL optimizations are available, could be used there. I don't expect any problem there. But of course, the parallel algorithm needs to be very specific to the semantics of the in-place language. I can imagine that Hensing has for instance, has a more complicated rule execution mechanism than ADL. So I expect that to be much more complex.
You make caches, and you expect the input patterns not to overlap. So
yeah, that's what I said at the beginning. That's a prerequisite for having that. Yes.
Yeah, well, thanks a lot, and congratulations again. It was a really nice presentation, nice work.
Okay, thanks.
Okay, next question by Apurvanand, please.
Thank you for the presentation. Currently I am working with like chains of model transformation. So my question is like, does this approach works for multiple model transformation also? Because like if we have two model transformations and they are properly chained, does that mean like I want to ask, like, converting immutable to mutable collections, is it feasible in multiple model transformation? Have you tried that?
What do you mean exactly by multiple model transformations? Can you explain that? Because I'm not...
Like chaining, suppose there is like from source to target model, we have one intermediate model that takes input from source model and produces output to the target model. So that is a chain of model transformation.
Okay.
So does this algorithm works in my case also?
Well, I mean, in a normal batch execution, I mean, in which the first transformation generates an output model and passes the output model to the other transformation, this of course works, because basically they are independent executions. But what would be interesting, I don't know if this is what you are asking, is to analyze the chain of transformations and try to perform optimizations to improve not only the individual execution times, but the whole execution time. This is something that we haven't done, but of course, all of this could be, all the type information, the rule analysis information could be used for that. For instance, I can imagine a situation in which you create a target element, and as soon as you have this target element, you pass this to the next transformation. So this is something that would be very, very interesting.
Yeah, like I'm like curious to know about like automatic collection thing, like converting from immutable collection to mutable. So there is some transformation for these collections. So will it be more optimized in transforming these collections?
Yeah, but these optimizations are within each different transformation. So basically, instead of what the optimization does is instead of having this, creates a piece of imperative code like this. But this is something internal to the transformation. I don't know if I'm answering your question.
Okay, this is specific to ATL. Suppose like in ETL or in other model transformation, is it not doable?
Yes, it is specific for ADL, yes.
Okay. Okay, and lastly, like, will you, can you share this slide to us?
The slides, you mean?
Yeah.
Yeah, of course, yes.
Oh, thank you.
Okay, let's go ahead. Next question by Massimo, please.
Yes, I will be short also because there are a lot of questions. I have a very small question. First of all, great work. Looks great. My question is this. It's about rules with multiple input pattern elements. So it looks like in your presentation, you were giving a view in which you were processing one element by each element by itself. So in the pseudocode, I saw something like execute element, something like this. So I found it a bit surprising. I don't know if it's a simplification that you're doing just for illustration purposes, or it's really a philosophical idea that elements should be processed one by one.
Yeah, I understand. No, I mean, it's both a simplification and a philosophical idea. It's a simplification because, yes, the idea could be is you have to implement a rule with multiple input elements, which is something that I typically don't see in ADL transformations. What I would do is to decompose the rule into something that matches one element and tries to and gets the second part of, like, you decompose the input pattern into one with one element and the other that performs all instances to get all the other instances of the pattern. You know what I mean? And the thing is that in this case, as far as I know, you don't need to create trace links because so you don't have this. Well, maybe you need to create trace links. I don't know. But the thing is that you can use the same strategy. You pass an element, and this element is in charge of executing the rule by creating like additional instances of the rule. I don't know if I'm being explaining.
Yes, I do understand. Well, it has a kind of an impact with. Sorry, you do this during the compilation, right? So the user can still
the idea is
write
to do that during the compilation. Yes.
Yeah, I understand.
But this is something that we haven't implemented. But that was the idea.
Okay, makes sense. Thank you.
Okay, let's move on first with the questions from YouTube by Yolande Philippe. So they are in the chat. I'm going to read them. Do you plan to extend the compiler to produce transformation working on distributed architecture for targeting bigger data sets and analyze your speed up with more than 12 concurrent tasks?
Yes, good question. So I think that was a possibility, but to be honest, so I would be I would appreciate a concrete example in which this is really needed, because in these transformations that we use, you see that this is the one that takes more time, and it is about 5 minutes. So I don't know if that's something that currently with the size of the models that we use makes sense. So I mean, I think that from a technical point of view, it is a very interesting challenge and something very interesting to do. But from a practical point of view, I'm not sure. So yeah, so please send me examples, and because I'm very interested on that, but I would like to know in which cases this makes sense.
Okay, thanks. And there is also the second question. Among your experiments, what was the transformation with the most complex rules? Arity of the rules, guard condition, complexity, and etc. So it's about complexity of
Yeah, I mean, from these ones, I guess. I don't know. It's something that I don't really know. Each one is a bit different, so we try to collect transformations with different styles. But typically in ADL, transformation rules are typically simple, and what it is complex is the OCL, the OCL code. So I don't know. So I really don't know.
Okay, good. Okay, let's come back to the audience here, and then the next one is Benedek, please.
I think Kurat was first, but so just the quick question. As far as I understood, these transformations are batch transformations.
Yes.
The question is, have you thought about how to adapt it to incremental transformations?
Not yet. I think that this is a good, this is a good line of work, because I think that with the key here is that if you have this static information about the transformation, which rules are called by which rules, then it would be possible to do to implement incremental transformations and do it in an efficient way. I don't know. I've seen many works in this line, and they are very good. So I don't know. It's a very, again, a very good thing to explore. But I don't know if it's. I mean, if what it is already there, it's enough and makes sense to do that. I don't know. But yeah, it could be very interesting.
Okay, and the last question is by Kurat, please.
Okay, thank you very much for the very interesting presentation. So the speed up table that I can see in the slides, does it include the overhead of like caching and indexing? My first question is this, and the second one is where you talk about the traceability links. Maybe I missed something, so can you say a few words about it, that how it helps in getting the speed ups, please?
Can you repeat the last one about the traceability links?
So maybe I missed that part where you talk about the traceability links. So you just like create a traceability link when it's required. So can you elaborate a bit how it helps?
Yes. So regarding the speed ups, I think that includes the pre-processing phase, but to be 100% sure, I should check the paper. What I remember is that we tried to do that in the best case for the other languages, the other engines. For instance, in ADL, these numbers, it's a bit complicated to explain, but what we do is to we do a heating phase before executing the ADL transformation to make sure that ADL has all the elements that needs to that needs for the transformation, instead of computing them lazily, because that so that it was in the best scenario for ADL. Like we try to emulate the pre-processing phase in ADL to have a fair comparison, because otherwise these numbers would be like, I don't know, 10 times bigger. So we try to do that in the best, in the best way for the other engines, but I should check. But typically the pre-processing phase is very little. But now I'm going to try to answer your question about the the trace links. I'm going to go here. So let's consider this this example. Imagine that. So in this example, you have two rules, package to package and class to class. And here, since this binding, or better, this rule is the results of this rule are needed in this binding, we need to create a trace link, right? The same here. For package to package, we need to create a trace link because the rule is, let's say, needed for this binding. But now imagine that we don't have this binding. If we don't have this binding, then we don't need to create a trace link for this rule because nobody is using its target element. This answer your questions?
Yeah. So you mean that if we don't have this binding, like we get this information from model, or
we get what we do is to we apply a tool called an analyzer, which is a static analysis for ATL, and what it tells us basically are these arrows here. An analyzer tells us this binding is using this rule. This binding is using this rule. So what we got, this allows us to reason in the way that I'm saying, that we can ask ourselves, this rule package to package is used by any binding? If the answer is no, we don't need to create the address link.
all right, so you just create, like by getting the information from the static analyzer, you just create the traceability links which you think would be required.
Exactly.
Like, yeah, all right, thank you.
Okay, so thanks, Jesus, for your presentation, for your answer, and for your presentation. So we are already in the last, let's say, 15 minutes of our workshop today. I think we use this the remaining time for extending the question answer time for the last presentation. So I would say that we can somehow it's up to you. I mean, we still have a few minutes, or if you have other questions or general comments, what I will do as a follow-up action, I will ask the presenters to share the slides if they like. So I will send them an email, and I will collect the slides and made available to the Lowcomote. Yeah, so I would like to, I think, yeah, just to conclude, I'm in the wrong switch. Yeah. Okay, so I would like to thank you all the attendees and all the speakers, and yeah, so thanks again for presenting. Thanks for your participation, and I think that we can conclude the meeting today. And you will find the stream, the registration on our YouTube channel, and yeah, so if you want to check again the presentations. Thanks again, and have a nice day.
Yeah, and thanks to you, Luca, for the great organization.
Also to the students that helped me to collect the links and have everything, let's say, ready to use. Yeah, I just did the last step. Thanks, then. Bye. Have a nice day.
Bye.
Okay, bye.
Thank you.
Bye.
Thank you.
Bye.
Bye.
Thank you.
Thank you.
Bye.